Hi everyone. Now we're going to start a new course on data structures in Python. So basically we will implement a lot of data structures like stacks, queues, linked lists, binary trees and a lot of other data structures also. And we are going to implement all of these data structures in Python. So all the videos on data structures will be like, first I will explain what are the applications of that particular data structure, and then finally we are going to implement in Python programming language. So in this tutorial we are just going to make a good knowledge of exactly what is a data structure and why do we require data structure. And from the next tutorial onwards we will start with our first data structure, which is the stack data structure, and we will implement it in Python. So let's start with the data structures. What exactly are the data structures and why do we need them? So basically we all know that all the programming languages, including C++, Java, Python, they all work with one common thing, which is the data. So the data can be in the form of some constants, variables like this, or stored in some files. So what happen is the most of the programming languages, they perform operations on this data. So I'm going to write perform operations on this data. So what are the operations you think can be performed on the data? So the first and the very important is the insertion. So we can actually insert some data, right? The second one is the deletion of data and updation of data, and similarly there can be more such operations like searching. So one important thing about data is that a data can be in a raw format, right? It can be a raw data. So in order to process raw data, it is very difficult to process raw data, right? So what we do is we actually make some structures, and these structures help us in performing these operations in a most effective way. So if we talk about data, what we do is, for example, in a binary tree, let's suppose I have data, let's suppose I have some numbers in here. Now you can see these numbers are just data. Now if I will put these numbers, let's suppose in an array, something like this, right? So I can push or insert some elements in this data structure. I can even try to update some values in this data structure. Now there are so many data structures available, and the reason why there are so many different data structures is that when you change the structure of the data, so the cost of operation, and when we are talking about cost, we are actually talking about time, because processing time plays a very important role in computers and in programming languages. We always try to write algorithms, and we also use some data structures, and these data structures should take least time possible so that we can actually perform these operations without giving some overhead to the processor. So whenever we have so many data structures like stacks, linked list, we will study about all of them in detail and we will also implement them. And similarly, we have binary trees, hash tables, etc. Now the reason why we have all of them is because in some data structures the insertion operation takes less time complexity. In some cases updation takes less time complexity. Similarly, we have some search operation also. So searching. So in some cases, in some data structures, we have searching, and the cost or the time taken by the data structure to do the searching of some particular element will be much easier and will take less time. So we will discuss such type of data structures, and basically data structures are the structures that are used to structure data or organize data organize data in a form of a structure. And why are we organizing data? Because to decrease the cost or to decrease the time taken, the processing time. Right, so that's our main objective. So the right choice of a data structure for different operations. For example, let's say there is a company, let's say Google, and we all know that Google has a search bar, right? So most of the operations that are performed is the searching operation. So in that scenario, there are millions of records or a very big amount of data that Google has. So in order to perform searching, we need or we require some data structure that will decrease the time complexity. We call this cost as time complexity, right? So the search operation should take less time complexity, and this is the main reason why we don't have any data structure which can perform all of these operations in big O of one time, right? So there are a lot of data structures which are optimized for searching, some are optimized for insertions, etc, etc. So from the next tutorial onwards, we will start with the stack data structure. First, we will discuss what is a stack. We will see how it organizes data, and then in Python programming, we are going to implement it. So first thing is, if you haven't studied Python, I have the Python course as well. I will give the link to the Python playlist in the description below, or it will come in an I button here. So the first data structure that we are going to discuss is the stack data structure. So basically data structures are used to give some form to a data, and by giving some properties to the data we can form structures out of them. Now using these structures we can do a lot of operations on them, which will basically help us in a lot of applications. So let's start with the stack data structure. So the first property that the stack data structure defines is the LIFO property, which is the last in first out property, which defines the structure of the data. So I'm going to show an animation video of how to visualize the stack data structure, of how insertion and deletion operation is carried out in the stack data structure. So last in first out means that the last element that goes inside of the stack data structure is going to become the first element to come out of the data structure. Mostly we call insertion operation or the insert element operation in the stack data structure as a push operation, and delete of element or deletion is known as the pop operation. So let's see how the stack data structure performs the insertion and deletion, and then we are going to implement this in the Python programming language, and I will use Python version 3 to implement this whole data structure. So first of all, let's consider that we have some elements. Let's say 3 is the first element that I have, then 8, 9 and 5. So let's say we have these 4 data, and now let's say I have a stack here. In this stack, what we are going to do is we are going to insert the elements one by one. First of all, we will pick the element 3. Now we will insert this element into the stack. The next element we will pick is 8, and then we will insert it in the stack. And similarly, we are going to do it with 9 and 5 also. So in this manner, we push the elements in the stack. Now let's say we want to perform the deletion operation. So let's suppose we want to delete the element 8 from the stack. Now the rule says that the last element that goes inside the stack can only come out. So in this data structure, if we want to delete the element 8, we cannot directly do that. We will first have to remove the elements that are on the top of it. So the step 1 is popping out the element 5. So we will pop out the element from the stack. Then the next element is 9, which is on the top of 8. So we will remove 9 also. And now since we can see that the 8th element is at the top of the stack, we can now remove the 8th element. And finally, we will again push back 9 and 5 inside of this stack. So in this manner, we perform the insertion and deletion operation inside of the stack. And the restriction is the LIFO, which is last in, first out. So we are only allowed to pop out the last element or the top element of the stack. Now this will be a lot helpful when we want to find out the recently added item to the stack. So now let's try to implement this whole data structure in Python. So I'm going to use Jupyter Notebook to implement this, and basically you can use any other IDE like PyCharm to implement this. So first of all, we will build a stack. So I'm going to just write a comment here that we will build a stack. And then one fortunate thing about Python is that it provides list implementation. So basically list can be used to build a stack, and we can use some predefined or inbuilt functions like the append function to perform the insertion operation. So the first thing that I'm going to do is, you can see I have created an empty list here, right? Empty list. In the next step, we are going to push some elements inside the stack. So now I'm going to use the stack.append function to push an element into the stack. So let's say we want to push an element 3 inside the stack. So first of all, I'm going to write in comment here that we are trying to push elements inside the stack. Alright, so now we will append some more elements in the stack. So let's try to append 4, 8 or 6, and like this we can append some more elements in the stack. Alright, so before appending these 3, let's say we are appending only 3 inside of the stack. So let's see how the stack will look like now. I will hit Control Enter to see the result. So you can see the stack has now 3 inside it. So now I will push some more element in it. So let's push 6 now. Again, I'm going to use the append function to push 6 inside the element. Now you can see 3 and 6 are there inside of the stack. So all the elements are going to push inside of the stack like this. Now let's try to push some more elements in the stack. Let's push 8, and similarly I will push one more last element. Let's push 7 inside this. Alright, so you can see this is the stack. This is how my stack looks like. So now let's say I want to remove 6 out of this stack. So there is no way I can remove 6 from the stack right away. We will first have to remove 7 and 8. So now we will have to use the pop operation to delete some element from the stack. So when I will use the stack dot pop function, which is the predefined function in Python, we do not need to implement it. What it will do is it will remove the item that you have added recently to the stack. So you can see the element that we have added was 7. You can see the 7 was added at the last. So after popping out, it will remove 7 from the stack. So if I will hit Control Enter, you can see it has removed 7 from the stack. Similarly, if we will make a call again to the pop function, it will remove 8 from the stack, and now you can see 8 is removed. And in this manner, we can actually pop out and push some elements into the stack. We're going to understand a very important data structure, which is linked list data structure. The concepts that we will study in this tutorial will help in understanding more data structures like binary trees, because they are going to be very similar to linked list. We will use references in binary trees and in further data structures. So it is a very important data structure to understand at this point. In this tutorial, I'm going to introduce you to what exactly this data structure is, and then we are going to uh, write the code in Python, and basically we will perform different operations on this data structure, which is this linked list, like insertion, traversal, deletion, etc. We will do them separately in separate videos. So let's get started. So first of all, linked list is a data structure in which we can arrange the items. Let's first consider some data items. Let's consider some integers. I'm going to take some random integers. Let's say 5, 4, 11, 8, and let's say one more, 10. So now we have 5 elements, which you can see here, which are basically data items. Alright, so in this playlist, we have already studied arrays, and we have seen how we can implement arrays in Python also. So what is the difference between storing these 5 data items in an array and in a linked list? We will also see that. So let's suppose I will draw a very small diagram here. Let's suppose we have this memory, and basically when we talk about memory, we are actually talking about RAM, which is the random access memory. And basically CPU will access this RAM and this memory space. So these items will get stored somewhere inside of these memory blocks. Let's say each block represents 1 byte, right? So I'm just drawing this simple diagram, and let's say there are so many blocks in here like this, right? So let's say this is a memory, and we want to store these elements inside of array. So when we use arrays, what happens behind the scene is these elements will get stored in this memory in a continuous manner. So arrays will store these elements in a continuous manner, right? So to store these elements, we will have to create an array of 5 elements, right? So when we will assign it, 5, 4, 11, 8, 10 will get filled inside continuous 5 blocks like this: 5, 4, 11, 8, 10, and 5, like this. One major drawback of this type of data structure is that we will have to make sure that the memory contains continuous 5 blocks for the data items. It may happen that in the main memory we do not have these 5 elements. So these 5 elements, 5, 4, 11, 8, 10, it may happen that inside of the main memory we do not have continuous 5 blocks, right? So let's say there are some data in this block which some other program is occupying, and let's say we do not have continuous 5 blocks, but we have in total of 5 blocks for which we can store these elements, right? So arrays will fail in that condition because they actually assign all of these in the single block. Now let's see what is a linked list data structure and how it will just improve this or optimize this memory optimization. So let's say we have these same elements, Now in a linked list data structure, what we do is we pick up the first element, which is 5, and this element is an individual element, and the next element, which is 4, is another element, and we call each of these elements as nodes. So if we want to say that the next element which comes after 5 is 4, we use a reference, which is basically a pointer, you can say, or it is basically a reference which will say that okay, at this memory address this node 4 is lying, right? So this is basically a reference. Now consider the next element, which is 11. We will say that 11 is a node, and we will say that there is a pointer which is going from 4 and it is pointing to this 11, right? So it is just like, let's say I want to store. Now let me remove these elements. Let's say these are not here. Now in a data structure like linked list, I can store 5 on this memory location. This whole memory space has some address assigned by the CPU, which are basically logical addresses. So each of these blocks have some address, right? So let's say the next element 4 is here. So what I will do is I will assign a reference which will say that from this memory location you will have to go to this memory location and you will find the next element inside of our data. Now you can see we have 11 as the next element, and let's say 11 is stored here. So now we will need another reference to point to this data node. That's why we call them as nodes, right? Because they are individual, or we can say independent data. And you can see the major advantage is that these are not stored continuously as it was in the case of arrays, and it will help us in actually saving a lot of space, because if we will assign these items in a continuous manner, it will occupy a continuous segment, and this will be a very big problem. Let's say we want to store 5 million data items inside of some memory, and in that case we will need a 5 million data block which are actually in a continuous manner. In that case, a linked list data structure will be very helpful. Now the next element is 8, so we will assign a reference to this 8 node, and then similarly to the last node, which is 10. Now let's understand some important terminologies in linked list which we will use when we will write the program in Python programming language, or even if you are choosing some other programming language, these terminologies are very helpful. So the first term that we have already discussed is that what are nodes? We know that. Now these references are also called as next pointers, right? Next pointers, and it is basically because it points to the next item inside of my data set. Now in a linked list can be of different types. It can be a singly linked list, it can be a singly linked list, and it can be a doubly linked list, and the final one is the circular linked list. In this tutorial, we will implement the singly linked list. In singly linked list, we have a single pointer, right? A single reference. In doubly linked list, we have pointers which are the next pointer, and we also have another pointer which pointed to the previous element, right? So we call it as a previous pointer. And similarly, we have this for all the items in a doubly linked list, and similarly there is a change in a circular linked list, but in this tutorial we will focus only on the singly linked list. So in the singly linked list we do not have this previous pointer, we do not have this here, right? we have only one single. So let me draw this diagram here again. 5 is here, then 4, 11, 8 and 10. So the first term is the nodes, the second term is this next pointer. When we will implement this whole data structure in Python, we will have to individually allocate these data items inside of the memory, and the way to do is to create a class node, and then we will create an object of this class. And as we all know that whenever we create an object of a class, it assigns that particular all the data inside of this class in the main memory, right? So we will use the classes and objects, our knowledge of classes and objects, to assign these nodes in here. Then we will use some references inside of this class node, and which will basically point to these next elements, which we will discuss in the further coming tutorials when we will study how to insert elements inside of the linked list. So the basic structure of a linked list contains a node, which is the data item. Let's say it's the data, and the second one is the reference, right? So let us write it as ref. One important term is here, which is that the last node of the linked list will point to a null reference, right? To a null reference, so that we will be able to understand that this is the end of the data set, and now we will have to stop traversing inside of this data set. So this is the null pointer, and we know that we can use none keyword inside Python to actually reference to a null pointer, right? One last important term is the head pointer. This head pointer is basically used to point to the first element of the linked list, so that we will know that from this node onwards we are starting the linked list. So it is a very important term, and we are going to implement this in Python. The first task is to create, let me write here, I will write a comment here. The step 1 is to allocate the data item in memory, right? We will have to allocate the data item in the memory, and the way to do is to create a class, right? So instead I will write create a node class here. So now let's see how we can create a node class. We will use the class reserved keyword, and the name is node followed by a colon, and we will press enter. Now in this node class, whenever we will create an object of the node class, we will have to specify the data item, right, which will be some integer in our case. So if you will see here, you can see here that if the element is 5 and we are creating a class node, the data should be passed at the time of object creation. This is a very important line that we will have when we are creating the object. We will have to pass this data to the object, and we already know that we can do it using constructors. You can understand the simple Python concepts in the Python playlist also. So I've given the link to that playlist and the playlist of data structures in the description below, so you can check that out if you want to understand the concepts and or you want to revise it, right? All right, so let's move here. The class node will have a constructor, and the way to define a constructor is to use the init with two underscores here like this. We know we pass two elements. One is the self, and the second one, let me just increase the size so the things will be clear now. All right, so the first element is the self and the second element is the data, right? So we are defining a constructor where we say that whenever you are creating a node class, you will have to pass the data It can be an integer or a character or in anything, but you will have to pass it. It is mandatory. So now we will define it like this. Now you can see that our node, which is here, this node 5 is the data, and we are passing it at the time of object creation. So whenever we will create an object of this node class, it will automatically create a constructor. It will automatically call the constructor, and it will pass the data 5 to this constructor. You can see there is a self also, which is basically a reference to the object which is trying to call this class node. All right, let's move on to the next thing, which is to define the constructor. In the constructor, we will create an item. We will use self.item to represent that whichever object is trying to call this node. We know that there are different nodes because we have different data items 5, 4, 11, 8, 10. So we need the self dot item to actually represent which particular call is actually we are actually referencing the self. We are using self to reference that particular call at the time of object creation, right? So we will create a self dot item, and then we will assign it the value of data. So let's say we have data as 5. So we will say that the item of that object, which is by using self, is equal to 5, right? That's the main objective here. So we know that in a node we have a data. The second important thing in a linked list, and more specifically in a singly linked list, is that a node will contain the data as well as the reference, right? So we will have to create a reference. Now see, we're not saying what is the next node, right? It will get assigned when we will create a new object of this node class. So let's see how to so we will have to create the reference, and we will assign it to null, right? So whenever you will try to add some elements or nodes inside of this singly linked list, you will have to assign another pointer, and it will also point to null. All right, so let's see how we can do this. Let's create a reference. I'm going to call it as ref, and initially I'm going to assign it as none, right? So none basically means it is a null reference, right? So it is pointing to nothing. Then if we will create another object, which is another node, then we will have to take care that we will have to reassign this reference ref to that node, which you can see here, that here if I've assigned ref to null and now I'm assigning a new item, I will have to make sure that this ref or the reference is not pointing to null but to this data node. This will become clear when we will study how to insert elements inside a linked list. Here we are just studying the structure of a linked list, and you can see the structure includes a node which has the item, which is the data, and the null reference. Next important task is to, which is our step 2, is to create the actual linked list, right? So we will create the linked list class, right? So we'll create a class which is the linked list, and this linked list class will basically represent the head pointer, which is here. We will assign it to null, and then we will keep on adding these nodes which will come from these node class. We will keep adding these nodes inside of the linked list, and we will also take care of the references when we are trying to add the elements, right? So we need some linked list class which can actually maintain this whole data structure, right? Because node is representing just the data and the reference, but our linked list class will hold the data of this whole linked list, right? So all the nodes connected together will form the linked list class. And we know that initially, since there is no data inside of the linked list, we will create a head pointer which is pointing to null, right? So Here I'm going to define a constructor, which is by using init, and then I'm going to use a self parameter. Now remember that the linked list is empty, so we do not need to supply any data. So we will leave only one parameter here. Now we are going to create a head variable, self.head. So whenever we will create an object of this class, we are actually assigning a head of that class, of that object, right? So that's why we are using self.head. And obviously we are going to assign it as none because initially the linked list is empty, right? So I can write here that linked list or double L is empty initially, right? So now we have a basic structure of our node class and our linked list. Now we will see in the next tutorial onwards, we will see how to insert nodes inside of this linked list, and we will also see how we can actually print them, right? So we will see how to traverse in a linked list. So basically I'm going to write here that the operations that we are going to perform is insertion, and then we will study traversal inside of a linked list, right? So in the next tutorial onwards, we are going to basically use this fundamental structure, which you can see these two steps are very important. We will create a node class and a linked list class. We will assign these references to null and this head to null, and then we are going to use this step, and we will move further to insert some more elements. Now remember, insertion can be of different types. Let's say I want to insert an element at the starting of the linked list. So we will have to be careful that if I want to insert some element, let's say I want to insert 6 at the starting of this point, I will have to make sure that this head reference is now pointing to this 6, right? In this way it will get added to the first position in the linked list, right? Similarly, we can define some specific index at which we want to place the or insert a new element, and we can also perform insertion at the end of the linked list, right? So we will traverse along the linked list, and whenever we will detect that the linked list is the reference is null, we will say that we have reached the end, and at that position we will insert our node. In traversal, we will just create a while loop which will jump from one location to another, and we will start displaying these values, and it will do it until and unless we have reached a null position. So that's what we are going to do in the next tutorial. Basically, first of all, let's also do the step 3, which is to which is basically to create the object, which is to create object of linked list, right? So now we will create a linked list. I will call it as a new linked list, or for simplicity I'm going to write it as new underscore ll, and then I'm going to create an object of the linked list class like this. So now you can see this new linked list has been assigned. It has a head pointer which is pointing to null. So from now on we will perform step 4, which is to insert element at the end of the linked list. Insertion at the starting of the linked list, right? So basically the code of this insertion at starting is of just 3 lines, but it is very important to understand how the references are working inside of this function that we are going to create, right? So first of all, here is the code that we have previously written. In this code, you can see I have created a node class which has a data and a reference which is initialized as null, because we are just going to create nodes with the help of this class, and then we are going to insert it inside of the linked list. In the linked list, it is initialized using a constructor in it, and you can see it has a head pointer which is initially pointing to null, and that is because the linked list is empty initially. We have seen that we will have to create an object of this linked list, and basically the object that we have created is new underscore ll, right? So now we are going to perform insertion at the starting of that linked list. So here I'm going to create a function, and I will name this function as insert at start function. And in this function, since we will have to do the insertion of some element, I will provide the element here, and I will also provide a parameter which is self. Self means it is an object of this linked list class, and it is just a reference to that object, and then I will also provide data, right? So here I will just use the object of the linked list class, and I will use the dot operator to call this function which is insert at start function, and inside this I will provide some data. Let's suppose I will provide 5 here, right? So we want to add 5 at the starting of the linked list. So we will have to define this function here. So let's see how the programming approach will be when we want to insert a data inside of a linked list. So as we know that initially linked list is initialized as a head pointer. We have a head pointer which is initially pointing to a none value or a null value. I will just write none here. Now linked list is empty. Now what I want to do is I want to insert 5 in this linked list, right? I want to insert 5. So what I want to achieve is I want to add the 5 node in this linked list, and then I will create another reference here which is actually going to point to null or none. So let's see how we will have to change these references in order to insert an element at the starting of the linked list. So first thing is, whenever we want to insert an element inside of a linked list, the first thing that we will have to do is we will have to create an object of the node class, right? So we will have to create an object of the node class, and we will have to pass the data, right? Here the data is 5, and we will create an object here which will be new node. And after creating an object of this class, we already know that whenever we create an object of a class in this way, we are actually trying to allocate it inside the main memory, right? So I'm going to write here allocate main memory. So behind the scenes of this line, whenever we initialize an object, this data 5 is stored inside of the main memory, and as we know that there is a reference null inside of this class, so actually we can see this type of implementation inside the main memory, which you can see here. It has the data, and it has a null reference here, right? So let's do our first task, which is to create an object of the node class, right? And the data that I want to uh, pass is this one, which is from this function data. So I will write data here. So that is our first task. Whenever we want to insert some element, we will first have to allocate it, and that is the main use of this node class. After we have allocated this particular object, what we just need to do is we just need to insert it inside of our linked list, right? So let's see the status of our linked list at this point. Now linked list has a head pointer which is pointing to null. Now what I'm going to do is the strategy that I'm going to use is just focus on this line here. This is the node 5 that I want to insert. The first thing that I will do is, we can see that here from the head node, whatever the reference of the head node is pointing to, you can see head is pointing to null initially, and let's say I want to add 4 after inserting 5. What I will do is, whenever I want to insert this element at the starting of the this linked list, I will just use the head pointer which has a reference to the first element of the linked list, and I will assign it to this new node which we are assigning here, right? So we want to insert an element, so the first task is to create a reference. I'm going to write here, the first task is to assign reference of head pointer or just head to the new node, right? So we will do this first and a very important task, which is to change the which is to just initialize this new node inside of our linked list by assigning the reference of head node to this node, right? So let's see how we can do this. Here inside of the insert at start function, I have the new node, and the reference of this new node is dot ref. I can use the dot ref operator. You can see that whenever we initialize an object, we have the data and reference, because in the node class you can see we have the data and we have the reference here. So the reference of this new node is actually assigned to whatever the reference of the head node was previously, which is self.head. Self.head means, self means that it belongs to the object of this linked list class, which is our new linked list, new LL, and head is basically the head pointer of this linked list class, right? So previously, wherever this head pointer was pointing to, we are just going to make sure that this new node will point to that location. That is just the main use of this line, right? So from this diagram, you can actually see here that in all the cases, the first task, let's suppose I want to insert 4 here. So what I will do is, I will capture the reference of the head pointer, which is self.head, which is pointing to 5. And then what I will do is, this 4 also has a variable. Initially it was null. Now instead of null, I am going to reassign it to point to the first node, right? So in the first step, we are actually trying to access the first node, because our main motive is to insert at the starting of the linked list. After we have done this, the last step is to just assign this head node to the new node, right? So assign head to the new node, because we know that the head pointer has a specific purpose inside of the linked list, which is that it will always point to the first node, right? So first node is going to be the new node. So here what I'm going to do in the next step is, I'm going to assign self.head, means I'm reassigning the head reference to the new node, right? So equals to new node. So now this pointer, this head pointer will point to the new node, which is the starting of our node, right, of our linked list. Now remember that these two lines should be in the specific order. If you will write this as, if you will assign this particular line before this line, it will create some differences, and that is mainly because if you will assign the self dot head, if you will assign self.head to new node first, then what will happen is, here you can see, when if you will try to assign this head pointer to the new node first, you will actually lose the reference of this head node which was pointing to the first node of our linked list. So you will not be able to assign the the pointer or the reference of a new node inside of the first element which existed inside of the linked list. So that's why you will have to make sure that these are in order. Now here you can see these are the three steps. Let's revise these three steps. The first step is to obviously assign the node, allocate it inside the memory. So I'm just going to write here allocate inside the memory. Then we will have to actually assign the new node reference, which is the reference of the new node, to the self.head. And we know that the head pointer is always pointing to the first node. So what we are just doing essentially here is we are assigning the new node to the first node, right? So reference to the first node. Here what we are doing is, now we know that the purpose of the head node is to point to the starting of the node. So we will reassign the head node to the new node. So in these three steps, in these three basic steps, we can actually insert the elements at the starting of the linked list. Now if we wish to insert some more elements, we can actually do this by changing the elements, let's say 4 and 3. Now after you will run this program, it will be able to allocate these inside of the memory. You are not going to see that in the output, but it has already done that. Now in the next tutorial we will study how to do traversal in the linked list, and when we will try to do traversal, we will be able to output the contents or all the nodes of the linked list in the particular order. Basically, traversal is just from moving from one node to the till the last node of the linked list, and we are doing so for different things. For example, let's say we want to search some element, and after searching, let's say we want to delete that element, or let's say at that position we want to insert some other element, right? So we will need traversal. So basically, let's suppose I have a linked list here which is 5, 6, 7, which has 3 nodes. We know that the last node is always pointing to the none value or the null reference, and these nodes are pointing something like this. And as usual, the head pointer is pointing to this node, the first node of our linked list. So we are actually going to use traversal by using this head node, which is, or we can say the head reference. And the idea is that when we are traversing in this linked list, we can actually access all the elements inside of this linked list. So basically traversal goes like this, and the last node is obviously pointing to the null node. So the idea is to access or try to reach each and every element of the linked list. And basically, since the last node is pointing to the null value, we can use it to actually know that we have reached at the end of the linked list, and we can actually stop the traversal, right? So let's see how we can actually do traversal in linked list, which is uh, we will try to access each and every element, and we will display the content of the node after each access. So while traversing, we are going to display the data inside of the node, right? So how can we do this in Python, right? Or in any other programming language? Basically, this is the data structures in Python programming. So we will be writing the code for in the Python programming, but the strategy will remain same in irrespective of what programming language we are using, right? So what we will do is we will use the head pointer because it is pointing to the first node. We will use it, and we will keep updating this head pointer until and unless the value of the head pointer is pointing to null, right? So we know that the head pointer is always pointing to the first node, so we do not want to mess up with the head pointer. We do not want to change the reference of the head pointer. So what we will do is we will create some temporary reference, which will be a variable, and we will assign it as head pointer. And then we can do is we can update this value of temp by reaching each and every element, so the head pointer will not get changed, right? So the first step is assign a temporary pointer which is pointing to the head pointer. Remember one thing, head is pointing to the first node here, so when we will write temp equals to head, temp is also pointing to the first node now. Now what we will do is we will run a while loop. Inside of this while loop, we can see that we will run this while loop until and unless the value of temp reaches null, right? So we will keep updating this value of temp from one element to the another, and when it will point to this null value, we can stop the while loop. We can exit from this while loop, right? So how to update this temporary reference? Let's see that. Now we know that each node has a data item and a reference ref, which is here, right? So what we will do is we will keep updating at each step. We will keep updating this temporary pointer. So now you can see at the first iteration, temporary pointer is pointing to the first node. I will assign it to the temp dot ref. And what happens when we do this updation is you can see that this first node has a reference pointer which will point to the next node inside of the linked list. So if I will write temp equals to temp dot ref, temp will get updated to this reference, which is temp dot reference will give me 6, right? Because temp is now pointing to this node. So now the temp will be updated here. So temp will go here, and again the while condition is checked. Now we can see that it is not null. So again we will update the value of temp, as now you can see temp is now pointing here. So temp dot ref will give me the next pointer, which is the next node 7, and we will update this temporary pointer to point to the last node, which is the 7th node. And again temp dot ref is, it will now give me null, and again I will update it. So the temp will be equal to null when we have reached the end of the linked list. And since this condition will go here, and when we will check it, the while loop will stop, right? So let's see how we can write this implementation in Python. I will open the Jupyter notebook here. Now you can see here we have created the new linked list. In the previous tutorial we have inserted three elements 5, 4 and 3, and we have inserted them at the starting of the linked list. Now we are going to perform step number 5. In the step number 5, we are going to call the traverse function. By using the linked list, we have the new linked list as the instance where we have all these three elements, right? So you can see new linked list dot insert at start. So this new LL object has these three nodes. Now let's traverse it. For that, I have created a traverse function, and here you can see in the class linked list, which is here, which we have done in step 2, I have created a function which is the traverse function. Here you can see that we are passing the parameter self here because it will point to the, it will give us the reference of the object, which is the new LL, which is the linked list we have created, right? So in this function you can see this is the code that I have written. First let's take a look at this condition here. This says that if the head pointer is pointing to the null position, so if self.head is none, we are going to print that the linked list is empty, and we are going to return from this function, right? Else, if it is not true, if head is not pointing to null, it means that there are some items inside of our linked list. The first step is to assign temp as the head pointer. You can see we have done temp equals to self.head. we have written the while loop that while temp is not pointing to the null position or while temp is not none, we are going to print the value, right? Where, or I can write that we are actually going to display the value here. So we will print the temporary pointer dot item, which is the data of the node where the temp is pointing to, right? We will leave a space here, and in the next line you can see from the indentation, or you can see from the spacing, that these two lines are belonging to this while loop. So within this while loop, what I'm going to do is I'm going to reassign or update the value of the temporary reference to point to the temp dot reference, which is basically pointing to the next node, right? So that's how we can do traversal, and if we want to perform searching, we can do it inside of this while loop. We can access each and every element here. In the next tutorial, we will see how to delete the elements from the linked list. If you will run this program, you can see here we are actually displaying in the output 3, 4, 5. So first, the 5 is inserted inside the linked list. Then at the starting of the linked list, 4 is inserted, and then 3. Right? So these are the contents of the linked list. How to delete a node from the linked list. Deletion from a linked list is uh, it's a little bit tricky because we are going to manage a lot of references to delete the element from the linked list, right? So please pay attention because it is not as easy as insertion, right? So what I'm going to do here is let's first take a sample linked list with some nodes. Let's say 1, 3, 5, 8, and let's take one more, and let's say this is our linked list. We know that the last element is always pointing to the null value or the null reference. The first node is having the head pointer, which we also call as the head node, and we have the regular references like this, right? So now let's say that I want to delete an element from this linked list. Let's say the element that I wish to delete is 5 here, right? Let's take 5. So we will call the delete function using the object of this linked list class. We will create the delete function inside of the linked list class, and then it will delete this element from the linked list. Alright, so let's see how we can delete the element 5. There are certain steps that we're going to follow. The first step is to actually traverse, right? We will first have to traverse to the node which we want to delete. Then only we can perform something on it, right? And we know that if we want to traverse to that node, we will first have to create a while loop which will run from the head node, and it will continue to update the temporary node that we will create, right? First, we will create a temporary reference which will be equal to the head reference, right? So now we have a temporary pointer which is pointing to the head node here, and we will keep updating the value of temp as temp equals to temp dot ref, which is the reference, and we're going to run a while loop which will go until and unless the value of temp is not equal to none, right? So we'll run this while loop and we will traverse in this linked list. But remember that we will have to stop this while loop, which is we will have to stop the temporary value to update to the next value whenever we will reach the node that we wish to delete, right? So in this while loop, you can see temporary initially it is pointing to this value 1, so it is not null. Temporary value which will get updated here, So now temp will point at 3, right? So we will keep updating the value of this temporary pointer according to a condition, right? What is the condition? The condition is that we are going to write, which is going to be the if condition, is that we will compare the value of the node that the temporary pointer is pointing to with the node that we wish to delete, right? So if temporary dot item, we know that if we want to fetch the data, we will have to use the item variable, and then we will compare it, which is by using the double equal sign. So if the value of temp is equal to the item that we want to delete, so let's say this is the D node, which is the node that we need to delete, right? So if this value is equal to the D node, which in our case is 5, so we will return out of this loop, right? Not return, we will break out of this loop. If we will write return, it will return out of the function itself, right? We do not want to return out of the function. We want to break this while loop. So what will happen is the temporary pointer will keep updating, but whenever it will reach this position, now you can see at this position, the value that the temporary pointer or the reference is pointing is 5, and the D node is also 5. So at that position, we will break out of this while loop. Now you can see that we have the position here, which is 5. Now we want to delete this element. So let's see what is the strategy to delete this element. To delete this element, we just need to update this reference, which is coming from the previous node, right? So let's say we want to delete 5. So this reference, which is the 3, we will have to update it. So I'm going to use a red marker that we want to delete this reference, and we will have to update this reference to point to the next node, which is here, right? So we will update this particular reference and we will update it to point like this. What will happen is that after doing this, we will get a linked list which will go from 1, then 3, then after 3 we will go to 8 and 9, right? So the resultant will be 1, 3, 8 and 9. So in this manner you can see we have deleted the node 5. Now in order to update this reference, we know that we cannot use the temporary pointer because we cannot access the previous reference of this using this temporary pointer. We can only access the next reference, right? So we will have to use a strategy, a very important strategy, so that we can stop this temporary pointer at the previous node of the node that we want to delete, right? So if I want to delete the D node, I'm not going to stop the while loop at the D node itself. I will stop it at a previous node, right? So let's see how I can do this. I can just update this condition, right? So this is not the condition that we want because we want to update the reference of the previous node. So we cannot use this condition. We will rewrite this condition as if temp dot ref dot item is equal to the node that we want to delete, which is the E node, then only we are going to break. Now let's see what happens when we are writing the condition like this. Temp dot ref means the next node, right? So initially our linked list was 1, 3, 5, 8 and 9. Our temporary node was here. Now what we will do is instead of comparing this value 1, we are going to compare temp dot ref. So the reference is going to be the next node, which is 3. Dot item means we are going to check the value, right? So if temporary reference is pointing to 1, we are actually going to check the value of the next node, which is 3. This is the basic meaning of this line, which you can see here, and we are going to compare it with the D node. So you can see this value 3 is not equal to 5, right? So now we are going to update the temporary node as temp equals to temp dot ref. So now the temporary value will get updated, and now temp value will come here. Now again this condition will be let's see this condition now, temp dot ref dot item, which means the item of the next node, right, which is 5. Now we are going to compare it with the D node. Since it is equal, we are going to break out of this loop. So now you can see that our temporary node, or we can say our temporary reference, is now actually pointing to the previous node, because we have changed the if condition in this manner, right? Very important step. So now what we are going to do is we know that we will have to update this particular reference, which is this one. We will have to update it. So what we can simply do is we can see that the temporary pointer is pointing here. So we can simply write that the next of this, or the reference of this node, will be equal to the is equal to temp dot ref dot ref, right? So what is temporary dot ref? Dot ref means temporary dot ref is pointing here, right? So we are actually updating this particular reference. So we are updating it. Temp dot ref means we are actually making it assign to the next and the next, right? The next of next. Dot ref means the reference of the reference. So temp dot ref, if you will read it like this, is actually 5, and dot ref means 8, right? Dot ref means the next element. So if this is 5, 5 is referencing to 8. So what we are going to do is temp dot ref is what, 3, and this means, and here also temp, we are going to reassign the temp dot ref to 8, right? So in this manner we can actually update and delete the node, right? And we already know that Python, using garbage collection, it will remove this 5 node because it has no references inside of the memory. So the resultant will be the linked list 1, 3, 8 and 9. So let's see the program that I have created here. You can see I have, in this line, I am calling the delete function with a value 5. Now let's take a look at the delete function itself, which is here, right? So first we have created a temporary reference, and just ignore this condition here, this part here, because we are going to discuss this part also. It is also very important step, which will be our last step to delete the element, because we are actually missing a case which we will cover in this condition. Now concentrate on this part here, which we have discussed. You can see here, while temp is not none, right? We are running the temporary pointer till none, and we have a condition here. If temp dot ref dot item is equal to D node, we are going to break out of the loop. Else we are just going to update the value of temporary reference, so that it will point to the node previous to the node that we want to delete. Now we will update the references, right? In order to update the reference, we will first have to see that the temp.ref is not null. If temp.ref, which is the next item inside of this temp.ref, means the next element to the temporary pointer, if it is null, it means that we have not found the element, which is obvious. And else means that we have found the element, and we are going to update this temp.ref equals to temp.ref.ref, which is basically the this condition that we have studied, right? So we will have to make this updation, and I have already told you how this updation is working. Now let's take a look at a very important step. Now here you can see delete 5. After this, I have inserted 1, 3, 4 and 5 in the linked list initially, and now you can see after calling the delete function on 5, it has removed 5 from the linked list. Now if I will write 4 in case instead of 5, and if I will run it again, you can see 135, right? So means 4 has been deleted. If I will write 3, it will again work. You can see now 1, 4, 5, 3 has been deleted. Now very important case here, if I will write 1, this is not going to work, right? You can see 3, 4, 5 is working because of this whole condition here that I have written. If I will not write this condition, right, let me just delete this condition here because we have not studied it yet. Now you can see that after this you cannot delete the element 1. If you will write delete 3, it will work. You can see it is working 1, 3, 4, 5 and 1, 4, 5, which means 3 is deleted. 4 will also get deleted, 5 will also get deleted, but 1 will not get deleted. It will show an error which says that none type object has no item attribute, right? So let's see what is the significance of this condition that I have written here, which is this one. Now you can see in this case, since we are actually comparing the value of temp.ref, which is the next element dot item, we are actually going to miss the first node, right? Because our comparison will always start from the next element, which means we are going to miss the very first node in our linked list. So if we want to delete the first node in our linked list, this whole part that we have done, it is not going to work. Why? Let me again rewrite the linked list here. Let's say we have a linked list 1, 3 and 8, 9, and now let's say I want to delete 1 from this linked list with the same approach that we have done before. We know that temp is pointing here. Now you can see that in this if condition, you can see temp.ref.item, which means that we are going to compare the next value, which is 3, but the node that we want to delete is 1, right? So this condition here which we have written, it will always miss the first node. It will always start from these next nodes, but it will always miss this node. And what will happen is, since the next node, which is temp.ref.item, is not equal to d node, the temporary pointer will point here, and this will go on, and when the temporary pointer will reach here at this point, and it will try to access temp.ref.item, you can see there is no item here, so that's why it is showing that uh, attribute error, which is none type. You can see here it is saying that none type object has no attribute, which is the main reason because of this condition that we have written here, which will automatically skip the comparison of the first element with our d node, right? So we will have to write a very basic condition, which is this one. Now this condition will take care of the first item, which is the head. So what this condition does is self.head.item equals to d node, which means that if the item of the head pointer is equal to the d node, what we are going to do is we are going to make an updation. We are going to make the head pointer point to the self.head.ref, which means the next pointer of head. which is actually the second node, right? So self.head.ref is the second node of our linked list. So we are going to update the head pointer to point to the second element. So now you can see here, head was initially pointing here. We will compare the value of head with the D node if it is true. What we are just going to do is we are going to assign this self.head to the second node by using self.head.ref, right? In this manner, you can see this element 1 is ignored. So our linked list will start from 3 from the head node 389. So the resultant will be 389 in our linked list. So that is why deletion is a little bit trickier, right? Now you can see this is the whole code that we have written in the linked list. You can get this code inside of the Android application that I have created for free, and you can download it, and you can also take a look at the notes that I've written here so that you will be able to understand it more. We are going to discuss about the queues data structure, one of the most important data structures, and it has a wide variety of applications which we are going to discuss today. So first of all, the first important point about queues data structure is that it follows the FIFO rule, and FIFO means first in, first out rule, right? A very simple and a very basic rule that this data structure follows. And as we all know that data structures are just data and the structure is defined using some rules. So in queues we have this FIFO rule. So it just says that the first element that goes inside of the queues is going to become the first element to come out of the queue. Now let me explain you this rule with a very simple example of a ticket counter, right? So let's say there are three people who want to buy a ticket, so they will form a queue, something like this, right? So now let's say the first person which is inside of this queue wants the ticket, so he will take the ticket, and you can see the queue starts from here, right? So I'm going to call this as the front of the queue, and you can see the queue is ending here, so I'm going to call it as the rear end of the queue. So the first person who has got the ticket and now he's going to get off the queue. So it means that the deletion operation takes place at the front end. So in case of queue, we call it as a DQ operation, not a deletion operation, right? So DQ takes place at the front of the queue, right? Now let's say we want to insert, there is another person who wants to join the queue to buy the ticket. So he's not allowed to join from the front or in between of the queue because that will be cheating. So he will have to go at the back of the queue, and now I'm going to update the rear to this last person, right? So this is the status of the queue. So similarly, if we want to insert some elements inside of the queue, insertion, which is the NQ operation, right, is performed at the rear end, and DQ operation is performed at the front end. Now this has a wide variety of applications that I will discuss very quickly. So first of all, this type of a system is also known as the first come first serve basis, which is FCFS, right? First come first serve. So the first person or the first resource that comes inside of the queue is going to get served first. Now this application is used in CPU scheduling. So if you have studied CPU scheduling, you must have studied the first come first basis, and it is implemented using a queue data structure. So the first element that comes inside of the queue is going to get served first, and that's why it is going to come out first, right? There are some more applications also. For example, we can use queues as priority queues, right, by assigning a priority to some function, and we are going to discuss priority queues. They are also known as heap data structure. We will discuss them in detail. And then we have some multi-threaded programming, right? If you have studied Java, you might, or C sharp, you must have studied multi-threaded programming. In that, the thread scheduling is a concept where we use the queues, right? So these are some of the applications of the queues. Now let's quickly take a look at how we are going to implement it in Python programming, or even in any other programming language. We are just going to discuss the basic idea, right? And then you can perform it in any language you want to, right? So the first step, right, we're going to perform some steps to make it easier for you to understand how to implement the data structure, and you do not need to just learn all the steps one by one. You will understand them very quickly. So first of all, in the first step, we are going to create a queue class, right? And then we will create an object of this class, which we will call as small q, and this object of the class is going to maintain the whole structure of the queue, right? Initially, I'm going to write here, initially when the queue is empty, right, we will create two pointers. The first pointer is the front pointer, and since we want the front pointer of the queue object, I'm going to write self dot front, right? Or we have self dot rear, and initially they are going to both point to the null position or the none position, right? So because the queue is empty initially, these two are going to point to the none position. Now step 2 is to create a node class, right? We will create a node class. So basically, since initially they are null, we are going to create a constructor of this queue class, which we can do by using init, which is the constructor of this class, right? We will create a constructor and we will initialize the front and rear as null. Now we will create a node class which maintains, right, whenever we want to create or add some element inside of this queue, we are going to create an object of this node class. So this node class will have two members, which is the data and the next pointer, right? So basically we are going to implement the queues data structure using linked list. Right, there are various methods to implement queues in Python. You can use collections also, but we are not going to use it because they are frameworks and third-party libraries. We are going to use linked list. You can even use stacks also if you're using C++ or Java. And here we are going to use linked list. So in a node class, we have the data and we have the next pointer, right? So now let's see how to perform enqueue operation, which is going to be our step 3. Right, we will code all of these in the upcoming tutorials. We will code this whole concept. I'm just giving an idea about how you can do it yourself, and from the next tutorial onwards we will discuss them one by one, right? So in step 3 we have the enqueue operation. The enqueue operation demands one parameter, which is going to be the data. So let's say I want to enqueue one inside of the queue, right? So initially front and rear was pointing to null, right? So front and rear, they both are pointing to null initially. Now what I want to do is, for that case, what I'm just going to do is I'm going to check if self dot rear, right? Self means we are pointing to this object queue, right? Because we are going to call this function using the object queue, right? So queue dot enqueue. So if this object is going to be null, right, or none, then what we're just simply going to say is that the queue is empty initially. So for that, what we are going to do is we will assign front and rear equals to temp, right? And what is temp? Temp is going to be our node, and to the node class we are going to just pass this data, which is 1, right? So it will create an object, a temporary object, which will have 1 as the data, and we also have a next pointer or next reference, and we are going to assign self dot front equals to temp and self dot rear equals to temp. We can actually do it in a single line by just writing self dot front is equals to self dot rear equals to temp, right? We can do it in a single line also, right? So this case is when the queue is empty. If it is not empty, what we are going to do is now you can see that after adding the first element, the queue, right, the object queue will look something like this. We have the one inside of this with the next pointer, and front and rear is pointing to this object, right? Now let's say I again call the queue function, right? Queue dot, this one is queue dot enqueue 1, and now I'm going to call queue dot enqueue. Let's see, we want to insert 2 here. So we just have to change the front and the rear pointers, and sometimes we have to change the next pointer of this node to insert the element inside the queue, right? We know that the enqueue is performed at the rear end, right? So what we are going to do is first we check if the self dot rear equal to null. So you can see rear is not pointing to null, it is pointing to 1 here. So we are not going to change front because front is going to be the same in case of enqueue operation. We do not change front. Now what we are going to do is there are 2 steps and they should be performed sequentially. First you will have to perform the first step and then the second step. So we are going to assign self dot rear dot next, right? What is the meaning of self dot rear dot next? Self dot rear, which is this one, is pointing to 1, and when I say dot next, this means that we are actually here at this position, right? So we are going to assign it as temp, right? Now temp will be equal to node 2. So temp equals to node 2, right? So self dot rear dot next equals to temp, which means that now temp is 2, so 2 will come here, and 2 also has a next pointer. So now you can see that rear is still here, rear was still pointing here. We have just inserted the value of temp, which is the node 2. We have inserted it in front of the in rear of just in front of this, right? Now since it is an enqueue operation, we do not change the front, we change the rear. So in the second step, I'm just going to reassign self dot rear, right? This self dot rear should point to temp, right? So I'm just going to write self dot rear equals to temp, right? So now rear is reassigned to this position. So after inserting 2, you can see the status of the queue object is going to be like this: 1, 2, next, and rear is pointing to 2 because it is inserted after 1, and front is pointing to 1. So that's how we do the enqueue operation. We will discuss the dequeue operation in a further tutorial, and in that also we will just change the front pointer, and we will have to make some more reference changes also. That it is the step 1. In the step 1, we will create a class queue, right? And in this class queue, the first thing I'm going to do is I'm going to define a constructor to initialize the value of self dot front and rear as null, right? So inside this we will pass self, and here I'm going to define self dot front is equal to self dot rear, right? And they both are equal to none initially because the linked list or the queue is empty, right? So I'm just going to write here queue is empty. Now in the next step, we are going to create let's create one more utility function, right? Which we will call as isEmpty function, which will actually give us the value of whether the queue is empty or not, right? That's why the name is empty. So if we are going to return true or false if the value of front, right, or the front reference is equal to null, right? So if front is null, it means that the queue is empty, so it will return true, which means that the queue is empty, right? So is empty is a utility function. So that's the first step. Now here I am going to create a object of queue by using queue class, right? Something like this. After doing this, what we need to do is call the enqueue function like this, and we are going to pass data 1 here, right? Now before writing the enqueue function, we will have to perform step 2 above this one, right? So step 2 is to create a node class, right? So whenever we want to insert some node inside of this queue, we will first have to define the node class, right? This node class will have a constructor. Again, I will pass self, and here I'm going to write self.data, right? So it will have two uh, values which will be self.data, and it is going to be the data, right? So to the constructor we are going to pass self and data also, so I'm going to write here data. And we have one more thing, which is the next pointer, right? And it is going to be null initially, right? Now this is the step 1 and this is the step 2. We have discussed them, right? We have the constructors ready, we have the node class ready. Now the time is to create the enqueue function, which is the step 3, right? So here remember that we will create the enqueue function inside of the queue class, right? So just make sure to leave the indentation right, or else it will give you some error, right? So in the step 3, we have to define the enqueue function, something like this. And this enqueue function is actually of the queue object, so I'm going to pass self, and it also takes the data, something like this, right? So now in the enqueue operation we have discussed, here you can see the steps, right? First we will have to define this case when the self.rear equals to null, right? Let's quickly define this case. If first of all we will assign a temporary pointer, right, or a temporary node, and we will pass the data to this node like this. And now we are going to write the case if rear or self dot rear equals to null. It means that our linked list or the queue is empty, right? If that is the case, then we are going to assign self dot front equals to self dot rear, and both of them will be equal to null, right? So it will be none. All right, so we have covered the second step 1 of this step 3 to create the enqueue class. Now what will happen if the queue is not empty? Then we will have to do these operations. We have already discussed these two steps in the previous tutorial, right? So let's define these two steps. So if this is not the case, if self.rear is not equal to null, then what we are going to do is simply we are going to say self.rear.next is going to be equal to temp, and self.rear is equal to temp, right? Two easy steps. We have discussed them here. We are assigning self.rear.next as temp, and self.rear we are reassigning the rear reference to point to the temporary node. So in this manner we can insert some elements inside the queue, right? So let's call some more, call this enqueue function some more times, like 2, and we will call again 3, right? This is the third time. And let's say we will define a print function or the display function which display the contents of the linked list, sorry, this queue, which we are implementing using the linked list, right? So here we have step 3, and I'm going to define the display function here with self, right? Alright, so let's define the display function which is going to display the queue. So we are going to start from self.front, right? If front is the front of the queue, we are going to start to display the contents from front, right? So it will be 1, 2 and 3. So we will check whether the front is null. In that case, we are going to exit out of this while loop. And now what I'm going to do is I'm just going to print the data of the front, right? So self.front.data. The next step is to reassign the front pointer, right? So I'm going to uh, assign it self.front is equals to self.front.next, right? So instead of changing the value of front, what we are going to do is we are going to create a temporary value, right, which we will call as temp2, because we do not want to change the front actually. So we are going to replace self.front by temp2, something like this. So it will be temp2.data, and here also we have temp2 is equals to temp2 dot next, right? So this is how we are going to display the contents of this. So alright, so after running this, we are getting some error here. You can see the error is in the enqueue function on the line self.rear.next equals to temp. Alright, so what is the error? None type object has no attribute next. Alright, so we will have to go here in the enqueue function. Alright, so I can see the error here. It is self.front equals to self.rear equals to, it should not be none, it should be type temp, right? So you can see it clearly here. It was equals to temp, and we did a mistake by assigning it to null, right? So let's again run this program, and here you can see it will display the contents of the queue. So in this manner we can insert the elements inside of the queue, and you can see how we are maintaining two variables, front and rear, and how we are assigning these references. So basically in the enqueue operation, these two steps are the only important steps. We are going to study about binary trees, and we are going to cover all the important points related to the binary trees topic. So far we have already studied data structures like linked list, queues and stacks. All of these data structures are basically linear data structures, which means that the data will be stored in a linear fashion in those data structure, which basically is a constraint as it gives us the time complexity of big O of n, which is in the case of linked list and stacks and queues, etc. Now, in order to make this time complexity much better, in order to reduce the time complexity, binary tree data structures are really helpful because they form a different type of a structure, which is a non-linear data structure. As we already know that data structures are just data, but they have different structures which gives them a different type of advantage. So in case of binary trees, if we try to perform a search operation or even some other operations, it can give us a very less time complexity, which we will see in a later bit. So let's try to understand how the data structure looks like. What is the arrangement of data? So let's consider we have this data first. And here, now let's say we want to insert this data inside of the binary tree. Every binary tree starts from the very first node, which is also known as the root node. So the first task in writing the program to create a binary tree is to assign a root reference which initially will be pointing to a null value, and then when we want to insert a value inside of the binary tree, we are going to make this reference to point to this node. Every node inside of a binary tree is going to have a same fundamental unit structure, which is we will have a node with some data, and we will have two different directions or two different memory references. The first one will be the left memory reference and the second one will be the right memory reference. Initially, when we are trying to create a fundamental node, this node is going to look something like this, and these references are going to point to the null values. Now, when we want to construct a binary tree, we are just going to push this node inside of the binary tree. So let's say we want to push 5 inside of the binary tree. We are first going to create this fundamental node, and we already know that we can create an object of this class node which will construct this object, and it will allocate this data and these two references in the memory. So 5 will be allocated with two references which are initially assigned as null, and we are going to make sure that the root is now pointing to the 5 which is the first node instead of null. Now let's say we want to insert some more data, 4 and 6. So here let's say I want to insert 4, and here I want to insert 6. And we know that when we want to insert any node, every node will have two different pointers and they are going to point to null. So we will have to make sure that the left memory reference will be referencing to the element that we wish to insert in the left part of the tree. So let's say I want to insert 9 in the left part of this. So I will have to make sure that first I allocate it by creating an object of the node class and providing the data by at the time of object call. I can just provide the data. Let's say I want to create a node 9. I can just provide the data 9 and I will create a constructor to construct this object. Whenever we create an object, we know that it is actually stored inside the main memory. So whenever we create any object of this node class, which we will see when we will program it in Python, it is stored inside the memory. Now after calling 9, we will have an object which has data as 9 and two null references. Now let's say we want to insert 10, 15 and 13. So let's say I will insert 10 here, I'll insert 15 here, and let's say I will insert 13 here. All the nodes we know will have two pointers which are pointing to null. Now since we do not have more data to insert in this binary tree data structure, all of these are going to be the null references. So here I am just using a null symbol to represent that these are null references. Now let's understand one important concept, which is what is leaf nodes. So here you can see a leaf node is a node which has the left and the right references as null. So 15 is a leaf node inside of this structure. And similarly 10 and 13 are also the leaf nodes because they also have left and right pointers pointing to the null values. So all of these data which is 13 and 10, they all are leaf nodes. Now let's come to the very important part, which is the height and depth of the tree. The height and depth of the tree is very important because it will help us evaluate the time complexity of different operations in a binary tree. So let's suppose, let's first come to the topic, which is the height of the tree. Height is calculated as the number of edges that goes from the root node to the node with the longest path. So here we can see that the longest path is from 5 to 4, then 9, and then 13. So from root to 13, we will calculate the number of edges, which is 1 from here to here, and then 2, and then 3. So there are 3 edges from root node to the longest path. So the height of this binary tree is equal to 3. Now let's come to another term which is also known as level of a binary tree. Level starts from 0. So at level 0 we have node 5. At level 1 we have nodes 4 and 6. At level 2 we have nodes 9, 10 and 15, and level 3 has 13. So this is going to be the level 3. As we can see here, if we want to find out the number of nodes inside a level, we can just do 2 raised to the power the level, which is 2 raised to the power L. So here 2 raised to the power 0 will give us 1. 2 raised to the power 1 will be equal to 2. So there are 2 nodes. Height of this binary tree is 3. Now let's consider what is a subtree. A subtree is a part of a tree which actually is not the whole part, but it is just a smaller section of the tree. So here we can assume that this is one of the subtrees of this binary tree data structure. We can also consider this one as a whole subtree. We can even consider a single node as a subtree. So these are the possible subtrees inside of this binary tree data structure. Now let's see how we can calculate the height of a particular subtree. So let's say I want to calculate the height of this subtree, which is 4, 9, 10 and 13. So we want to find out the height of this subtree. We will apply the same concept that we were applying to the height of the whole binary tree. We will consider this as a whole binary tree. So we will start from the root of this subtree, which is 4, and then we will move to the longest path, which is 13. So the height of this tree will be equal to 2. Now let's move on to another important term, which is known as the depth of the binary tree. Depth of the binary tree is defined as the number of edges from the root node to the node that we wish to calculate the depth of. Now let's say I want to calculate the depth of 6, or let's say here I want to calculate what is the depth of 4. So from the root node to 4 we have only one edge, so the depth of this node 4 is going to be the value 1, which is the number of edges from root node to the node which we wish to calculate the depth for. There is a huge confusion between the height and the depth of a tree, so I will like to clear that. Height of the tree is actually number of edges from the root node to the last node of the longest path, whereas the depth is the actual number of edges from the root node of the tree to that node. So that's how we can calculate the depth of the tree and the height of the tree. Now let's take a look at how this tree is going to be stored inside of the memory. As we all know that all the data is going to get stored inside the memory. So the first thing is I'm going to draw a structure of memory here. And we know that memory is divided into several continuous blocks which can store some data. Let's say each of these can store 1 byte of data. We know that the memory is actually, it has memory locations which are continuous in nature. So for example, I'm just assuming that this memory starts from 1001 and goes 1002, 1003 and so on. Now we can see here that binary tree is actually having 2 branches, but it is not the way it is stored inside the memory. It is going to get stored inside the memory in a different fashion. So let's say we first create an object of the node class by allocating 5, which will allocate 5 in the main memory, and it will have two pointers, which is left and right, which is initially pointing to a null reference. Now let's say we wish to enter 4 inside of the binary tree. So let's say 4 is allocated here. Now programmers do not have control over where you can store a particular element inside of the memory because it is unknown where the memory block is empty. So here let's assume that 4 will be inserted at this memory location, which is 1003. Now we know we have a left pointer, so what we are going to do is this left pointer will get assigned to this memory location. So this left pointer will hold the value of 1003 to tell that this is going to be the left part of the tree. Now the right part is 6, so let's say 6 is stored here. So similarly we are going to create another pointer which is right, and right is going to have the value of 1002. We are just assuming these values, these are not the absolute values, we are just assuming them just for the sake of explaining how a binary data structure is stored inside the memory. The memory is a linear data structure, but we can use references to actually get this hierarchical structure. Now let's come on to the very important topic, which is different types of binary trees. The first type of binary tree is known as the degenerate or the pathological tree. A degenerate or a pathological tree is a tree which actually can be used as a linked list. So let's insert the elements, these same elements inside of a degenerate tree. So we have the first element here 5, then we will insert 4, and the right part is being null. Right part of every node will be equal to null, and we can only insert it in the left part. So after 4, 6 will be inserted here, and then 9 will be inserted here, and then similarly 10, 15 and so on. We can also do the opposite, which means that we can also insert the elements on the right part. In that case, the left references are going to be null. Now you can see the height of this particular type of tree is going to give a time complexity of big O of n, because you can see that it is actually a visualization of a linked list as a binary tree. Next binary tree, which is a very important binary tree, and it has a lot of applications in data structure, is known as a balanced binary tree. A balanced binary tree has a difference of the height of left and right subtree at most 1. This restriction makes every a binary tree as a balanced binary tree. So whenever we are given a binary tree, we try to make sure that it is a balanced binary tree, because it will give us a time complexity of big O of log base 2n. And the reason for this is that a balanced binary tree has a height equal to log base 2n. That's why the time complexity will be equal to log base 2n. So now let's see how a balanced binary tree looks like. In this example, let's see whether this is a binary tree or not. So this is a binary tree. Let's see whether it is balanced or not. So here you can see I have this node here. The height of the left part of the subtree is equals to 2. So height of this tree is equals to 2. Let's consider the right part. The right part has a height which we can see here. From here to here we have the height is equals to 1. So height of this will be equal to 1. So the result is actually equal to 2 minus 1, which is equals to 1. The difference should be at most 1, which means that it cannot exceed 1. Here we can see that it is not exceeding 1, So this is a balanced binary tree. Such type of a tree can give us a time complexity of log base to n. This application is actually very useful because in case of degenerate or linked list, we are having a time complexity of big O of n, which is greater than the time complexity of log base to n. So we prefer a balanced binary tree. There are certain variations of a balanced binary tree which we will study in the further tutorials, which is the red-black trees, then the AVL trees. So we will study them in detail in the upcoming tutorials of this course. Now let's understand the third and the very important part, which is a perfect binary tree. A perfect binary tree has 0 or 2 children in all the nodes. An example of a perfect binary tree will be something like this. This is an example of a perfect binary tree. This is also an example of a perfect binary tree. I can extend this more, right? We can have 2 or 0 children. It is also a perfect binary tree. This one is also a perfect binary tree, and so on. Now let's perform the implementation of binary tree. In the next tutorial, we will first create a class node, and what we will do is we will create a binary tree with the root reference initially pointing to null, and then we will keep on inserting these nodes to form a binary tree. Before moving on to that, we first need to understand a very good variation of binary tree, which is known as a binary search tree. Binary search tree is optimized for searching operation. So if we want to search a particular element, we are going to make sure that the left part of the tree will have the value of the node should be greater than or equal to the root node, or we can say the parent node. And for the right part, the value of the node will be less than or equal to the root or the parent node. We can even do the opposite of this to obtain a binary search tree. Binary search tree with these restrictions makes the search operation optimized. Let's see how. Let's see how we can insert this data inside of a binary search tree. So first we will insert 5 as the root element. So here I will insert 5. Then we have 4 here. 4 is having a value lesser than 5, and we say that if the value of node is less than the parent, it is going to go to the right side of the tree. So 4 will go to the right part. Then we have 6. 6 is greater than 5, so 6 will be inserted here. Then let's consider the next element, which is 9. 9 is greater than 5 and is also greater than 6. So if it is greater than 6, we know that it is going to come to the left part of the tree. Then we have 10. Now 10 is greater than 9. So again it is going to come to the left part of this tree. Now 15 is also going to the left part. So that's how we are going to insert the elements in the binary search tree. So in the next tutorial, when we will try to insert the nodes, we are going to form this type. We are going to use these restrictions to insert the node in the binary tree. And this will actually is an optimized search, because you can see here, if I want to search 9, first I will go to the root node. I can evaluate whether 9 is lesser than 5 or not. If it is greater than 5, I know that I do not need to traverse to all these elements which will be there inside of this tree. We will do that again and again recursively, ignoring the branches that we do not need to find or traverse through, which makes this optimized search. So basically in this tutorial, we are going to perform two important tasks, which is to create a node inside of a binary tree. Now let's move on to the very first step of creating a binary tree, which is I've already told you that every data structure has a fundamental unit which we call as a node. In case of linked list, we created a class node which will have only two elements, which is the data and a next pointer. Inside of a binary tree data structure, we know that every node contains data and also two pointers, which is the left and the right pointer, which are pointing to the left and the right subtree. The first thing is we will create an object of this class node. So we will have to define a constructor using the init function, which is actually the constructor. And here we will pass a parameter which is self. We have already discussed the importance of self, because whenever we create an object of a class, this self is actually a reference to that particular object. And we will also pass the data of the node that we want to construct using this constructor at the time of object creation. So here, for example, I'm just going to write a comment here. We can create an object of this class using node, and this will call a default constructor, but we can see that the default constructor has data. So let's say I want to push 5 inside of this node. So this way the data will have a value of 5. So every time we create a node, we are not interested in how that node is stored inside of that memory, because object creation does that automatically. The next step is to assign the data of the object as the data that has been passed to the constructor of this class, and then we will create two important pointers. Self.left is going to be a null pointer, because initially we are just trying to create a basic node which will have data, and two pointers which are going to be the self.left and self.right pointers, like this. In Python, we use none to represent a null reference. In the future, we are going to just make sure that we reassign these references to the other nodes in order to form a tree. So that's our first step. Now let's move on to the second important step, which is to create a class binary tree. This class binary tree, we will create an object of this class, will have a root reference. Initially it will point to null, and as we will keep on inserting elements inside of this binary tree, we are going to make sure that that particular object is actually maintaining the whole arrangement of all the nodes that we are going to create using this class node. So simply I'm going to create a class binary tree. This class will have a constructor, so whenever I will create an object of this class, it will call this constructor, and we pass a self parameter inside of the constructor, which will tell that this actually is a constructor. This is called by some object. Now we're going to create a root parameter. We know that root represents the first node of the binary tree. So in our binary tree, initially it will be none, which means that our binary tree is empty. Now what we need to do is we need to do some important steps. The first one is we first need to create an object of this binary tree. I'm going to create a new underscore bt as an object, and here I will simply write binary tree and two circular brackets, which will create an object. Now you can see that it will automatically call the constructor, which is this one, which will create a root reference. Self means that this new bt object, which is this one, has a root reference which is initially pointing to null. So that's the significance of self. It is actually a memory reference to the object that has called this constructor in it. Now let's see how we can insert some data inside of the binary tree. So we will create a new function which will be the insert function, which I'm going to define inside of this binary tree. Now before moving on to the insert function, we will first have to understand how to perform insertion and what are the constraints that are required while we are performing insertion of nodes inside of this empty binary tree. So here, initially in the step 1, we have already seen that we have created a class node which will actually create a node with some data and 2 pointers which are initially pointing to null. And we have also created a root reference which is actually pointing to null initially. Now this binary tree is actually empty initially. This is our step 1. In step 2, what we want to do is we want to perform insertion of nodes. So let's say I want to insert a node 5 here. So now since we know that our binary tree is empty, we should the first condition, which is a very important condition, is to check whether the root node or the root reference is empty or not. If it is empty, we are simply going to make sure that this node is actually, first we will create a node using the class node here by passing this object 5 with the data 5. So it will create a node 5, something like this. And then what we're going to do is we will reassign root node. Initially it was null, so we will reinitialize it, and it was now going to refer to this node, which is this one. So now it will create our first node inside of a binary tree. So let's see how the function call is going to be and how we're going to perform this important step, which is to insert a node inside the root element. Alright, so we are going to use the object of the new BT, which is the object of this binary tree, because we want to perform all the insertions inside of this object binary tree. So that's why we are actually calling the insert function using this object, which is new BT. To perform insertion, you will first have to understand what are the things that we require to perform insertion. The first thing is obvious, we need data which is going to be inserted. The second thing is I want to pass the root node or the root reference of this binary tree. I can do that simply by just using new bt dot root. Now the reason why we are doing this, it will become more clear when we will write this insert function, because we are going to use recursion inside of this insertion function, which will reassign this root node to the left or the right node depending on the condition. But here at this moment, I'm going to make this concept abstract. So just assume that in the insert function, we are passing the data only. Now inside of the insert function, we first have to write a parameter self, which actually says that this insert function is of the new bt object. Now what we want to do is we want to have a data here, and we have a reference which is new bt dot root reference. I'm going to write it that this is actually a reference ref. Now the first condition that we already saw here in the slide is that first we need to check whether the root of this binary tree is null or not. So if it is none, it means that the binary tree is empty. What we are simply going to do is we are going to first create an object of the node class passing the data, which is 5, and to reassign self, we will have to reassign the root node. We will do it like this. So now what this line does is it will simply create, or I should write specifically, it allocates a node, and root is referencing to this node. Now let's see what is the use of this reference parameter and how can we insert more elements inside of this binary tree. To insert some more elements, I'm going to make more calls to the same function but using a different data. So here I will write 5, 7, 13 or 12 maybe, and let's make one more call using 15. Now we are going to make sure that the insertion operation which we are going to perform makes this binary tree as a binary search tree, right? So we are actually creating a binary tree, but there is a slight variation of binary tree which is known as binary search tree, and it actually optimizes the search operation of inside of a binary tree. So let's see how these elements are going to get inserted inside of a binary search tree. So we wish to insert some more elements. So here you can see I've made a call 4, 7, 12 and 15. 4, 7, 12 and 15. Now initially we have a root node which is 5. Root is pointing to this node which we have done in step number 2. This is going to be the step number 3. Now let's see how to insert 4 inside of this root. Now what I'm going to do here is I'm going to assign two conditions to perform the insertion operation to make this binary tree as a binary search tree or a BST. What are these conditions? The condition says that if the value of the node that you wish to insert inside of a binary tree has a value which is less than the value of root node, right? So you can see here, if we want to insert 4, we will first compare it with the root node. Now you can see the value is lesser than 5. So what we are going to do is we are going to insert it at the right part of the tree, right? So 4 will get inserted in the right part of the tree. Now let's consider the next element, which is 7. So the second condition is that if the value of the node is greater than the value of the root, we are going to insert it in the right part of the tree. These two conditions are very helpful because they actually make this binary tree as a binary search tree. So every time we want to perform a search operation, we can actually leave one branch and it will save a lot of time complexity. So here 7 is going to get inserted inside of a binary tree. Now let's see what is the next element, 12 and 15. Before moving to insertion of these two elements, which is a very different strategy we are going to use, let's see where this 12 will insert it. Now 12 is first compared with this element root node. 12 has a value greater than 5. So it will have to be inserted inside of the left part of the tree. But now it is observed that the left part of the tree, which we can access using root.left, now this is going to be the left pointer. So this left part of the tree already has an element stored in it. Now what we want to do is we want to insert 12, but we cannot insert 12 here because 7 is already there. So what we are going to do is we are going to make sure that we create a temporary variable which initially is actually a root value or a root reference. So temporary variable is actually a reference to the root node, and what we will do is we will reassign it to this part which is here, and now this temp node is pointing here. Now what we can do is we can use the same strategy which we have used in case of root. We will compare the value at this temporary node with the value that we want to insert, and now we know that 12 is greater than 7, so it is going to get inserted at the right part of the tree. We will keep changing this temporary reference. Here in our programming case, we have actually not used temp as the variable name. We have used reference as the name. So what we are going to do is we are going to make sure that this reference is assigned to left or the right part according to what insertion we are going to perform. If we want to insert the element at the right part, we are going to make sure that reference is actually pointing to the right part of the tree. Things will become more clear when we will implement this. So let's start the implementation part. Now you can see I have, in all the cases, I have passed a second parameter, which is the root parameter. So initially we are at the root position. We observe that root is not null. So now we will write another else case here. If the root is not null, what we are going to perform? Now since the binary tree has a root node, the first important task is to actually create a new node. We can do that by just calling an object with some value, and we know that the value is the data. So in this way we have allocated the data, but still this data needs to be inserted at the right position, which is according to the conditions which we are going to apply in the case of binary search tree. So let's see what is the condition. The first condition is if the data that you wish to insert is less than the node.data. So what is node.data? Sorry, it will be ref.data. So you can see that I am passing the root reference to this variable ref. This ref temporarily holds it holds a reference to the root node. So what this is going to do is it is going to check whether the data at this reference is initially pointing to root. So root.data is actually 5 in our case. So if the data, which is 4 here, if we want to insert it inside of the tree, we are going to compare it with the root.data initially. If it is less than this, we will have to write a very important condition. Now here, if the data is less than the root.data, we have already written the condition here that if the value is less than, we are going to insert it in the right part, right? So if we want to insert in the right part of the tree, we will first have to check whether the right reference of the root node is empty or not. For that, I'm going to write a very important condition here inside of this if statement. Make sure you are actually using the right indentation between the if cases. So this if case is when the data is less than the ref.data. If the value of reference dot right is not none, right? It means we are actually checking because we want to insert the data on the right side of the tree. We will have to check whether it is pointing to null or not. If it is pointing to null, what we can do is we can perform the insertion operation, and how we can do that is by making a call to the self.insert function. And in the insert function, what we are going to do is we are just going to pass the data, and we are going to pass the reference dot right. Now let's see what is the meaning of this line and why it is necessary. Here you can see ref.right is not none. It means that there is some element which is already there inside of the right part of the tree. So let's consider here. So initially we have this 5 node at the root position. I will pass this root reference to the insert function. So we have another reference ref which is initially pointing here. And now what we are checking is we are checking that ref.right part if it is null or not. Now let's say there is actually some element with, let's say there is some element x here. If it is there, what we are going to do is we are going to reassign this reference to the reference dot right, which is here. So this is reference dot right. So how do we reassign this? We are reassigning this by passing the argument ref.right. So here you can see that in the insert function we have the data, and then we have ref.right, which is actually the right part of the tree. So when we will pass this ref.right, this is actually a recursive call. This is actually a recursive call to the insert function, and this recursive call, when we will make this call, this ref.right, which is pointing to the right part of the tree, it is now going to get passed to this ref, which will make the reference ref point to the right node instead of pointing to the root node. Again, we are going to check whether that root node is null or not. Since we already have the right part as not null, we will again reach here, we will allocate the node, and we will again check whether the data is less than or not. Now here, let's say the data is less than x, so we are going to insert it on the right part of the tree. So here, let's say we want to insert y, so we can insert y here, and we know that when we want to insert y, we will first have to check whether the left part is null or not. We are only going to perform insertion when we have a null position. So let's write the another case here, which is the else case of this part, which means that if the right reference is null, then we are going to perform the insertion operation. Now the way to do is we are just going to make sure that ref.right is actually pointing to the root node, sorry, to the new node that we have created. This new node is the node that we wish to insert. So what here we are trying to do is, here we are trying to reach to reassign, to keep reassigning this reference to the right part of the tree by making recursive calls to this insertion function, which will keep reassigning the reference until and unless the reference is actually a null reference. If it is null, then we are going to make sure that the reference is pointing to the node that we wish to insert. So that's the whole crux of insertion. Now, since we have done this, the second part is very easy. We are going to just copy this whole if case like this. And now we are going to just simply paste it here. Now in this if case, which is here, we are just going to change it to greater than ref.data, and instead of right, we are going to write here left, and here, since we want the reference to the recursive call should go to the left part because the data is greater than the root node or the ref.data, we will keep this recursive call again and again. It is going to call because the value of the ref.left is not null. At the point when we will reach at the leaf node where it is going to be null, we are just going to make sure that we assign it to the left part of the tree. So that's how we perform insertion inside of a tree. In this tutorial, we have seen how to insert these elements in a binary tree, and because of the two conditions, which was that if the value of the node is greater than the value of root node, we are going to insert at left, else we are going to insert at right. We have obtained a binary search tree here. Now there are three types of traversals in a binary tree, which we are going to cover in this tutorial, which is the in-order traversal, pre-order traversal, and post-order traversal. So traversal is basically an operation where we try to traverse or try to access each and every node inside of the binary tree. This can be used for the sake of performing the search operation or to display the contents of the binary tree. So we will write the Python program in this tutorial. After we will cover the conceptual part, we will write a program in Python which will be able to display the content using these three traversals. So the first one is the in-order traversal. In in-order traversal, we first traverse the left part of the tree, then we traverse the root, and then we are going to traverse the right part of the tree. It is known as in-order traversal because root is in between left and right, right? So that's why that's a simple way to learn these three traversals. In pre-order, since it has pre in it, pre means first, so root is going to come first here. And then we have the other two, which is left and right. So we are going to write it like something left and right. In post order, post means at the last. So first we will write left, then we will write right, and then finally we are going to write the root node because it is at the post, right? Post means at the last position. So in this way we have these three types of traversals. Now let's see how the items are going to get displayed in each of these cases. In in-order traversal, we first traverse the left subtree. So let's see in this example. Here you can see that this is actually the root node, and this part of the tree is the left subtree, and this part is the right subtree. So I'm going to represent it by two small variables L and R. Now in this part you can see, since in order we traverse the left part, so we will keep traversing in the left subtree like this. And after the traversal, you can see we have reached this last node, which is the leaf node, since it has no values here. Now what we can do is we can display the value of this left node, which is going to be 15. Now comes the root part. So after displaying the left part, we will have to display the root. So the root of this left node is 12. So we will display 12. Then we will have to display the right part of this subtree, which you can consider here, which is this one. So right part contains nothing, so we are going to leave it as it is. Now again we are going to go to the left part. Now you can see this is 7 here. So now I'm going to write 7, which is in the left part of the subtree. So the idea is very simple. We are going to traverse to the left subtree. We will go till the end. We will display the value. We will then display the root node and then right node. Then again we will go to an element which is above that, and then we will display the content of it and then the right part. Now since here you can see there is no right part here, I am going to come to the root part again, which is 5. So I am going to display 5 here. And now comes the right part. Now we have covered the left part. The root part is 5, the right part is 4. So in this manner in-order traversal works. We first traverse to the left part and we keep going on doing this. So how can we achieve this type of traversal using Python programming? We are going to create a function which will be an in-order function, and initially we are going to pass it a reference which will be the ref reference, and this reference is actually passed as the root node. So we are going to pass the root reference of the object of the binary tree by using new underscore bt dot root. And since this reference is initially going to point to the root node, we first want to traverse to the left part of the tree. So the first condition, which is very important, is to check whether root is null or not. So I'm going to write here, if root is not none, then only we are going to proceed with the traversal. If root is not none, we are going to make, first we want to traverse the left part. So in order to traverse to the left part, we are going to make sure that this reference, which was initially pointing to the right, to the root node, is now going to traverse to the left subtree. For that, we are going to make a call, a recursive call to the in-order function. And here I am going to pass reference dot left because we want to traverse to the left part of the tree. Now this recursive call is going to happen again, and it will call this in order function again, and which will check whether the root is null or not, and again it will reassign the reference to the left. So the reference variable, let me represent it with some other variable. Let me choose some other color to represent that. Let's choose a red variable. Now here reference will get reassigned from root node to here because of the recursive call, and we are going to do this again and again and again until and unless the condition, which is this one, evaluates to be false. In this manner we can actually get the traversal will be happening at the left subtree, and we will reach this node 15 here, and then we can display the value. So here we will display the value of print reference dot data. After we have done the print, we will print this. We want to print we will have to see how to print the root node. This print ref.data will print the root node, and now we want to do the last part, which is to traverse to the right part of the tree. For that, we are going to call the inOrder function on the right side of the tree, which is ref.right. So the idea is very simple. We are just choosing a pointer reference which was initially pointing to the root node, and we are just using recursion to reassign this reference so that it will be able to reach the left part or the right part according to our conditions or the statements that we have written here. And in between, we are going to write display the root.data or the reference.data, so it will keep printing all the items in this fashion. Let's take a look what will happen at pre-order and post-order. In pre-order, we will first display the root. So reference is pointing to the root, so it will display the root, which is 5. So here, in case of Python programming, in pre-order, we are first going to print reference.data, something like this. So the first thing is that we want to display the data. Then we are going to traverse to the left part. In the left part, you can see we have 7. So we are going to print 7. Now we are not going to print the right part, because if we will print the right part, the left part of this subtree is still there. So first we will have to cover all the left sided part, or all the nodes which are on the left part. So after 7 we will have to display 12, and then we will have to display 15. And now we will come to the right part because there is no nodes available, and now we can display 4 here. So here you can see this is the root, and these are nodes are actually left, right? So this is root, this is left, and this one is right part. So that's how we can perform pre-order. In pre-order, we will first display the data of the reference. Then we are going to move to the, since this is a pre-order function, we will create a pre-order function. And we're going to do similar to what we have done here, which is give it a reference to the left part first, and then give it a reference to the right part. So very easy and simple to understand. Now in post order, we will first display the left, the right, and the root node. So first we will go to the left part of the subtree to the last element, which is 15. Then we will display the right part. There is no right part here. You can see that this node is empty here, so we are not going to display anything. Then we want to display the root. The root is 12. And then we want to display the left part. So the left part is after 12 we have 7 here, so we are going to display 7. Now we want to display the right part, which is 4. And finally we have the root, which is 5. So from here you can see that this is the root part, and all of these first 3 elements, these are the left part, and 4 comes to the right part. The same strategies we are going to apply in programming also. First, we are going to make a call to the post order function. Since we want to traverse to the left part first, we are going to write reference.left, and then we are going to write reference.right. So I will write post order reference.right because we want to traverse to the right part, and then we are going to write print root. And we know that root is actually reference.data, which we have in here. So now let's see how this works in Python programming. So I will move on to the Jupyter notebook here, and I have already written the code so that it will be easier for you to understand. So you can see here I have given 3 calls here to the in-order traversal, the pre-order traversal, and the post-order traversal, and all of that we are giving the new bt.root as a reference. Now these function calls are going to call these 3 functions here, which we have defined inside of the binary tree, which is these. And here you can see that I have taken a variable root. You can take any other variable we can see that we have taken in this example we have taken ref, but here I've written root, so no problem. Root is going to play the same role. And now you can see I've written a condition here, if root. This means that if it is not null, right? So here, for example, you can also write if root is not none for better understanding, but this is also appropriate. Now we are going to make a call self dot in order traversal root dot left, right? So we are going to traverse left part, we will display the root part, and then we are going to display the right part. So this is how we can perform in order, pre-order and post order. We just need to write these lines and we can just rearrange them. So in pre-order the root comes first, then left, and then right. And similarly in post order we have the left, the right, and the root. You can see a very important term here, which is end equals to this separator here. This is known as separator. What it will do is, after displaying each and every element, it will display a space so that we can take a look at the data very clearly, right? So it's a pre-processing or a formatting technique. So after you will run this program, you can see that these are the results, right? So here we have the in order, the pre-order, and the post-order. Now you can see a very important and an interesting thing here, that in case of in-order traversal, all the elements are arranged in the decreasing order. So 15, 12, 7, 5, 4, they are in the decreasing order, and this is happening because we have inserted in a fashion of a binary search tree. Since in a binary search tree, we are inserting according to these two conditions, which you can see here, if data is less than ref.data and if data is greater than ref.data, we are going to insert the element to left and right part respectively. And due to this reason, the binary search tree in order traversal will give a decreasing format. If we want the increasing format, we can change these two conditions. If I will, instead of uh, greater than, I will do this, and here I will do less than. So if you will invert the symbols, you will be able to achieve this. Now you can see they are now in increasing order. So that's a very simple and nice technique. If we want to perform the sorting, we can actually also use a binary search tree, and this will also help us in performing the search operation, which will take log n time, because we know that in a sorted manner, if we run a binary search in here, we can see that it has a time complexity of big O of log n. In this tutorial, we are going to start with the heap data structure and we will implement it in Python. So basically a heap data structure is a binary tree representation of a given array. So let's assume that we are given this array which has these items, which is 2, 15, 4, 30 and so on, and we are also given the index positions of these array. Now what I want to do is I want to actually represent it in the form of a binary tree. So if we want to form a binary tree, we will call it as a binary heap. So I'm just going to write here binary heap, because this heap or this binary tree that we're going to draw here is actually a representation of this given array. So the first thing is how to construct this binary heap. We actually have three rules or three conditions which we will use to represent this array in the form of a binary tree. The first rule says that the root of the binary tree will be equal to the array and the position of this root will be equal to 0. We have a second rule which says that the left child or the position of the left child is going to be the array. We will multiply 2 multiplied by I, where I is the ith node where I wish to find out the left child, and then I'm just going to increment it by 1, and this is how we can get the left child. So the binary tree is, we are going to build it by using these conditions. So whenever we want to assign an element to the left child, we are just going to take out the position by using 2 multiplied by I plus 1. And similarly for right also we have a very similar construction. which is we are going to use the array 2 multiplied by I. I is the ith node. Instead of 1, we will write 2 here. If we want to calculate the parent node of any child, we can do so by just using array, and the position of this node will be equal to I minus 1 divided by 2. Alright, so now let's use these three rules to construct this binary heap. The root of this binary heap is going to be 2 because that is the position of the array. So here I am also going to write that this is the root, and I will write the position in square brackets here. So this is actually 0. Now let's see how to get the left and the child nodes of this binary heap. To get the left child, we have this formula, which is 2 multiplied by I. I is the position of the ith node. You can see the position of I is 0 in this case, right? So I is the parent. So this is 0. So 0 multiplied by 2 will give me 0. And the final position we will get is 1, and at one position we have the element 15. So here I am just simply going to write 15 and the position is going to be 1. Similarly, I will use this formula again, and now we will have the value 2 here. So at the position 2 we have the value 4 here. Now we have understood a very simple pattern here. Instead of recalculating the values using this formula, we can use this 0, 1, 2 and then 3 will come here, then 4 will come here, and then we have 5 and 6, so 5 will come here and then 6 will come here. Alright, so let's see what are the elements at these specific positions. So we have 30 here, and at 4th position we have 18, at 5th we have 6, and then finally we have 25. So this is the binary heap that we have constructed from this array. This heap is particularly not useful. So in order to make it useful, we have two different types of heap that we can build. The first of them is a max heap, and the second one is the min heap. Now the max and min heap are very useful when we are trying to implement a heap as a priority queue. So here you can see I have written it in the brackets here, which is a priority queue. A priority queue is a queue where the first element of the queue will have the highest priority or the minimum priority or the maximum priority. It is based on what we choose out of these two options. So what is a max heap? The property of a max heap says that the value of the parent node inside of the binary heap will always be greater than the values of the child nodes, right? So whether it is the left child or the right child, the value of the parent will always be higher. In case of min, we have the opposite condition, which is lesser than. Now let's see how we can build this max heap, and we are going to in this tutorial we will just use max heap. We can just invert these conditions, these operators, and we will obtain a min heap. So let's see how we will write the algorithm in Python also to basically understand how to implement this max heap. So what I just want to do is I want to convert this binary heap into a max heap, which has this specific property, right? So the first thing is I need to find out, we will create a function which is a heapify function, and let's call it as a max heapify function because this is a max heap. Alright, so now we have to decide how to max heapify, from where we should start the max heapify function, and then we will use recursion to do it for the rest of the elements of this binary heap, right? So the general rule is that the max heapify function will start from this node here, right? So if we have any type of tree, we are going to start from this node. Now how we can reach this node is the main reason why we are not starting from the leaf nodes. You can see that these are the leaf nodes, and the leaf node, at the leaf nodes we do not want to call the heapify functions. So in order to avoid that, we will have to start the max heap from the one child above the leaf nodes, right? In order to reach this position, we have a very simple formula, which is n floor division 2 minus 1. Alright, so here n specifies the size of the given array. So what is the size of the given array? Here you can see we have 7 elements as here. So n is going to be 7. N divided by 2, which is 7 divided by 2 is actually 3.5. But since we are using in floor division 2, what it will do is, because we are not interested in these decimals, it is going to remove these decimals and it will give me the value 3. Alright, so here you can see we have the value 3 here as this value. Now what I will do is I will subtract it with 1, so now I will get 2 here. So now we are going to call this max EP5 function at this position 2, right? So this is what we have got from our given array, and it will hold true for all the given arrays. This is a general formula which is actually used to ignore the leaf nodes and to start from this position. So now you can see we can start from this, or we can even start from this position as well. So we will start from this position because after that we can actually move here, which is 1. So we will start with this position, which is 2. So now max EP5 will come at this place. Now what we want to do is we will, whenever it will call it, we will call this max EP5 function on this position 2 according to this formula. Now I'm going to assign this node as the largest element. Now this is obviously not the largest element. I am just going to assign it as the largest, and in the future I will reassign it to the element which I found greater than this element. So the way to do is I will first check it with the left node. Here you can see the value of left node 6 is greater than 4. So now the largest will get assigned here. So I'm just going to show that this is now going to be the largest element after we will check a condition. Now what we will do is we will check the right part. In the right part we have 25. Now we will not compare with 4 here because now the largest is reassigned to this value. So we are going to compare 25 with this value, which is 26. Now 25 is greater than 26, so now the largest value is going to point here. So that's how we keep reassigning these elements to find the largest element. Now largest is pointing to the largest element. What we will simply do is we will simply swap it with the parent value, which is 4 in our case. So here I am going to show a swap symbol here. So we are actually trying to swap these values. So after I call the max EP5 function, I will just reassign the largest value. That's the second step. So I'm going to write here reassign largest. And the third step is very simple, which is to swap the values after we have found out the largest element, right? So we will write a swap function which will basically swap these values. So after this, after the first iteration, the max EP5 will build a max heap for this subtree, right? So we will obtain a max heap here. Now what we need to do is we will have to perform this max EP5 function on all these nodes, which is 1 and 0. So we are going to call this function max EP5 on 2, and then we are going to actually write a for loop, which basically what it will do is it will start from I equals to n divided by floor division 2 minus 1, and it will go till the value of this I is equals to minus 1, and at each position I am just going to make sure that the value of I is decremented by 1. So now max EP5 will start from 2 because we have calculated here it was 2. In the next iteration, the value of I will be decremented by 1. So max EP5 will be called at this position, which is here. So I'm just going to write that this is where the max EP5 function will call, which will finally build a max heap at this subtree. And then finally we will again decrement the value of I, and the max EP5 function is now going to point here, and it will finally build a max heap. One important property of a max heap and a min heap is that in case of max heap, at root you will get the maximum element, which you can see obviously in this case also, because we are writing the conditions and we are swapping the values. So at root we obviously got the largest element out of all the children, and in case of min heap we are going to obtain the minimum element. So this is the theoretical part of binary heaps, max heap and min heap, and we have discussed this algorithm now. So let's try to implement it here. So here I'm just going to write a comment that this is a heap implementation. Alright, so the first thing that we need to do here is we will have to first write the driver code. The driver code is basically the code that is going to execute all the functions here. So the first thing we need to do is we are going to create an array. and let's name this array simply as ARR, and let's insert the elements that we have chosen from the previous tutorial, or let's just assign anything here. So I'm going to write 2, 66, 30, 5, 9 and 10. So these are the elements of the array, and now what I will do is I will create a variable n. This variable n is basically going to get the size of the array, which we can use the function length, and here I'm just going to write the name of the array, which is here. Alright, so now we have the size of the array. Now the next task is to build a max heap. So here I'm going to write here build a max heap. One important thing is that this whole code will be available on our website thinkxacademy.com, so do check it out after the end of this tutorial. Alright, so now we know that we will have to create a for loop, and this for loop will run from I, and it will go till the range which we are going to specify that initially the value will be n float division 2. We have seen that -1. This is where the range will start, so the I will have this value n float division 2 -1. The second argument here, which I am going to write here, is going to be -1, and this argument basically says that we will stop when the value of I will be equal to -1. And the last element is the -1 also. The last parameters of this range function specifies that it is actually the value of I is going to be decremented by 1, right? So this argument here is going to decrement the value of I by 1, and this here is going to check whether the value of I is greater than -1 or not, right? So here we have the for loop, and now what I'm going to do is I'm going to make a call to the heapify function. And to the heapify function, first we need to actually give some indentation here, and then I will call the heapify function. And let's make this function as a max heapify instead of a heapify. To this function I am going to provide the array as the argument, the size of the the size of the array, and then I will be the position from which we wish to start the max heapify. And finally, in this driver code only, I am going to display the elements of the array. So let's quickly do that. So here I will just write print array, or let's say the max heap is, and here I will just create a for loop that will go from I in range n, and every time I'm just going to print the value of array 1 position here, right, array I. And what I'm just going to do here is it will be separated by a comma also, right? So this says array is not defined because A should be capital here, right? And now here we have the max heapify function. It says that this is not defined, so let's define it here, right? So here we have the max heapify function. Now let's create this max heapify function. So I will just type max heapify, right, and let's define it. So the way to do is use define max heapify, and here I'm just going to simply write all the 3 parameters that we were passing to this function, which was the array. So it was ARR, and the size of the array, and the position. Now simple task, what I'm going to do here is I'm going to create a variable which is the largest variable, and this variable will be equal to the ith position, right? So here we have this largest value here, which basically is actually pointing to the root element. Now what I'm going to do here is I'm going to create 2 more values, which is left and right. So left equals to, we know the rule to calculate the left position is 2 multiplied by I plus 1, right? We have already studied it in the previous tutorial. And obviously we will have to remove these semicolons because we are actually programming in Python, not in C++. So here we have the right position, which will be equal to 2 multiplied by I plus 2, right? So we have created two positions, left and right. We have assigned the largest element. Now what I'm going to do here is I'm going to create a if case, and in this if case I'm actually going to check whether the largest value so far, so largest so far, is compared with left child, right? So here we are going to do that. So in here what I am going to do here is, first of all, let's leave some space here, and here we have the define if case. The way to do is we are first going to write left should be less than the size of the array. That's the first condition, and the second condition is that the value at the largest position should be less than the value at the ith position, sorry, the left position, right? So we are actually comparing it with the left child. So what we are just doing is we are actually trying to compare it with the left child here with the largest element. If we find out that this largest value is actually less than the left value, since we are building a max heap, we will have to reassign the value of left, sorry, the largest value, because we are concerned with the largest value and it is going to point at left. Alright, so now what I'm going to do here is I'm going to write the second condition, which is also very simple. We're going to say that the largest so far, so let's say now the largest is assigning to the left. After that we are going to compare it with the right, so it is compared with the right node or the right child here. So the way to do is also very simple. If the right is less than n, that's the first condition that we need to check, and we also need to check the value of array at the largest position is less than the value at the right position, right? So we are just checking, we are just finding out and assigning the largest value in the whole subtree, right? So here we are reassigning the largest to right. So what we have done is we have just find out the largest element, and now what we need to do is we want to swap it with the value at the ith position, right? So now we are going to first write a condition, right, which is here. We will have to change the parent, and the way to do so is, first of all, I will just check that the largest value is not equal to the ith position, right? Because in that case we do not need to swap. If the value of largest is already pointing to the parent, we do not need to change the parent or swap it with the largest value. Now we are going to write the command, write the line which will actually swap it. The way to do is very simple in Python. Array ith position, then the array largest position, right, is going to be equal to the array largest position, comma, array ith position, right? So this simple line is going to just make sure that we will swap the values of the array at the position ith, which is the parent or the root, with the largest element which we have actually calculated from these two conditions. So now this function is complete, but we need one more step, which is to make a recursive call to this maxep5 function, because we need to call this function on the root nodes or the child nodes as well, right? So here I'm going to write recursive call In this recursive call, I'm just going to call the max heapify function, and I will give it the array, the value n, and the largest value. So now what it will do is it will again max heapify, but here instead of ith position it will start max heapifying at the largest position. So here what we are just trying to do is make sure that the heapify function is being called on each and every child node also. So this is going to make the recursive call, and this will actually make the whole subtree as a max heap, right? So we need to make sure of this important recursive call here. So now the code is final. Let's try to run it. First I am going to just save it, and now let's run this. Here I'm going to just write the command python 3, name of the file is heaps.py. Alright, so you can see here maximum recursion depth exceeded in comparison. So what I'm going to do here is I'm just going to exit it from here. So let's see what is the actual error that we are getting here. Alright, so I can see the problem here. The problem is in this line, which is this recursive call. The reason why this is happening is this max heapify function should be called only when we are changing the parent. So it should actually be indented inside of this if condition. So in Python it is very difficult to actually do the indentation part. You are going to actually see a lot of errors because of this. So this is how it should be written. It should be inside of this case. So we are going to actually call the max heapify on the largest part only when the largest is not equal to the node that where we want to perform the max heapify. So let's change this again. So let's try to run this program again. Alright, so you can see here this is the max heap. You can see the first element, which is at the 0th position, is 66, and you can see it is the largest of all the values of our array. So indeed it is a max heap. Our program is working, and now you can see the first element on the left side it will be 9, and on the right side we have 30. And we are going to just do this again. We can convert this heap to the array again, and you will observe that it is a max heap, right? Then what we can do is we can use this max heapify function to also perform the heap sort. Graph data structure is very important because it is used in a variety of places, and it has a lot of applications in the IT industry as well. So if you are going to apply for interviews, this topic is very important because it is going to come in the interviews a lot of times. So let's start with the graph data structure. Let's see what exactly is a graph data structure. The first important point that I will write here is that graph is a non-linear data structure, right? So it is a non-linear data structure. So far in this course, in this data structures course, we have already discussed a lot of data structures. Like we have studied about binary trees, linked list, stacks, queues. All these data structures are actually, they just contain data, right? So let's assume a binary tree. So here I'm going to draw a very simple binary tree, and let's suppose we have some linked list also, right? So these data structures we have already studied about them in detail. Now these contain only data, right? So I'm going to write here a very important point which differentiates them from the graph data structure. They contain only data. What type of data? It could be any type of data. It could be integers or characters or anything like that. But a graph data structure is very important because it not only contains the data, it also contains the relationships between the data, right? So here I'm going to write a very important point, which is relationships among data. So now let's assume a situation, right? I'm going to assume a very simple situation here. Let's say there is a very popular problem which we are going to discuss here, which is a traveling salesman problem, right, which will come in a lot of interviews. We're not going to cover the whole problem, but here I will give you a gist of what exactly and where exactly you can use this whole data structure. So traveling salesman problem is very simple. It says that there is a salesman, and this salesman is actually, he wants to travel from one city to another to actually do the sales work, which is to actually sell something, some stuff like that. Now let's assume there are 5 cities, I'm going to say, which is A, B, C and D. And there are some distances between these cities. From A to B there is some distance, from B to C there is some distance, and we will have to find out how exactly the salesman will be able to reach from let's say city A to city D in the shortest path and all of that stuff. So here graph data structure comes, and it is very important. This data structure is used to find the shortest path also, right? So there are wide range of applications. Now let's understand what exactly this second point that I have written here, which is relationship among data, means. Now here you can see we have 4 different cities. Let's draw these 4 cities here, which is city A, city B. Let's assume this is city number C and this is some city D, right? So these are actually cities, and what I want to do is, all of these cities has some distance. Now obviously these cities are data because they are the names of these cities. One important thing is, if we will not choose a graph data structure, if we will just concentrate on data structures like linked list and binary trees, basically we can connect them. Let's say I want to connect them using a binary tree. What we can do is we can connect like this. So A is the parent node of B and C, and let's say D is a child node of C. So this is a kind of binary tree, right? I'm going to visualize this something like this. So this is A, this is B, this is C, and here comes D, right? So a similar representation. Now the thing is, if I want to connect B to D, I can connect here, but I cannot connect here B to D. And there is one more which is important thing, which is relationships. Relationships is important because in most data some data is actually related to some other data. For example, city A is connected to city B, but there is a relationship which is the distance. Let's say 5 kilometer is the distance between city A to city B. In these types of data structures, which is the binary trees, the linked list, they won't work, right? So in that we are actually going to need the graph data structure. Now how a graph data structure looks like, and how can we convert this problem into a data structure? So a graph data structure contains a set of vertices and edges, right? So a set is represented by curly brackets. So this is some graph G. Let's call this graph G, and it has vertices and edges which are represented by V, right? So V is the vertices, right? Or I should say set of vertices, which I can represent something like this. Let's say we have vertex 1, then 2, then 3, and so on. The second one, which is the important one, is the edges. Edges are basically used to connect the vertices, right? So edges basically connect the vertices. Both of these, which is vertices and edges, they make a graph, a data structure. So let's see at this position. Here you can see A, B, C, D are actually the vertices of this graph, which is like this: A, B, C and D. Now let's see what are the edges. So you can see we have an edge that goes from A to B, which has data 5. So 5, AB is a vertex, sorry, AB is a edge here. Then we have BD. So BD is again another edge. Then we have DC, and then we have CA. So in this fashion, we can actually represent a graph. A graph contains of two very important things, which is vertices and edges. And these edges can also have some values, right? So I'm just going to write here values. These can actually have some values. For example, in this case, the distance was the actual values. Here we can have different values. Now basically there are different types of graphs available. So the first we are going to different two classes of graph, which is actually the undirected and the directed graph, right? So we have these two graphs, which is undirected and directed. Now if we want to show the relationships among data, what we can do is we can use a directed graph to do so. For example, we can say that you can only travel from from city A to B, but you cannot travel from city B to city A. So this arrow represents that. Now let's say you can move from this place to this place, then you can use a double arrow. So this is a directed graph. If we provide directions from vertices to vertices, this is known as a directed graph. Undirected graph is a graph in which we do have vertices, we also have edges, but we do not have any specific direction. So here we can have AB and BA as well. So here if we talk about undirected, we can have both the directions. There is no restriction, but in directed we have a specific direction. For these types of data graph, graphs, we have different set of problems which we will cover in this data structure series also. Now let's see how we can represent a graph data structure in programming, right? The first way is to use adjacency matrix. The first way, which is the easiest way, is to use a matrix which is a adjacency matrices. This is actually a 2D array. So what the idea is very simple. If you want to represent a graph, what you need to do is, let's say you have 4 vertices. So you will create a 2D matrix of size which is 4 by 4, which is something like this. And here I am going to basically create a matrix here which will have 4 by 4 places. So we have 1, 2, 3 and 4 places here, and we have 4 rows as well, right? So we will create a 2D matrix like this, and we know that we can use the positions to actually specify each and every position in a matrix. We know that the position of rows start from 0, 1, 2, 3, and then we have 0, 1, 2, 3. Now we have 4 vertices here, A, B, C, D, and we have this matrix. Let's see how we can represent this graph using this matrix, right? So we can create a directed as well as undirected graph from using this matrix. We are going to fill this matrix with zeros and ones, right? 0 represents that there is no edge from a particular vertex to another vertex. So since we have a 4 by 4 matrix, the first row will represent A, and this will represent B, this position represents C, and then we have D here. And similarly for columns also, we have A, B, C and D like this. So let's take a look at this first position, which is here. This position is 0 to 0. 0 to 0 means A to A. Now there is also one more possibility, which is there may be a case where A is related to itself. It will happen only in a directed graph. So if there is actually this type of self direction, we call it that. Now here, since there is a direction, so we have a cycle which goes from A and it also ends at A. So this is I am going to assign it as 1. Now consider A to B. Now there is a direction from A to B, and you can see it is 1. So I can actually write it as 1. Now what I can do is from B to D, right? So just find B to D. So B is here, D is here, just find the intersection, which is this one. I will write it 1 here. Then from D to C, so D is here and C is here. So this is the position. I will again mark it as 1. Then final one is C to A. So C is here, A is here. I will mark it as 1. All the other positions I am going to mark them as 0 because we do not have any directions in all those cases. Right? So now you can see how we can represent a whole graph data structure using a simple matrix, and this is how we feed the data in the matrix. One important thing is, if you have a magnitude, for example here from A to B, I know the magnitude is 5. Instead of using 0 and 1, you can even fit the data here. So instead of putting 1 here, I can also put 5 here. Since we also have a direction from B to A, I will write this should be also 5. So I will write 5 here. So in this manner, we can construct a graph data structure. There is a second way also. The second way is also very easy, and it is actually going to be a adjacency list. And we will discuss why these two different approaches, what are the benefits of using one of these approaches. We will discuss that. The first thing about adjacency list is that here we are going to actually use a list type of data structure, which is linked list, to represent a data structure, a graph data structure. Now the way to do is, I am going to create a list for 0, which is for the vertex A, which is in our example, and here I will just create this, and then what I will do is, the next node is B, so I'm just going to create another node which is connected to B, right, and I will feed the data here. And similarly, if we have direction from B to A, what I can do is I can create a circular linked list also, right? So we have many other options, but mainly we used a list structure to actually connect all the dots one by one. So we want to connect the vertices, we will connect them one by one using these types of node data structure. So for similarly for B, I can do that also. I will create a node, I will create a next pointer, and we will do it again and again unless all the nodes which are connected to B are inside of this list, right? So for each node we are actually going to maintain a list. This is the second method. Let's see what are the advantages and disadvantages here. Now in the case of adjacency matrix, if we want to update a particular value, it will take the time complexity of big O of 1, because we can access any position by just supplying, let's say this is the matrix M, and let's say I want to update the value of A to B. So what I can just do is, A is represented as 0 and B is represented as 1. So I can just update it to, let's say, 10 kilometers. So that's very easy in case of matrix, but in case of linked list, we will first have to just traverse through this linked list one by one, and this is the main reason it will give a time complexity of big O of n, right? So these are two things. The second thing, which is a disadvantage of adjacency matrix, is the space complexity. So obviously you can see there are so many zeros here which are unnecessarily occupying the space, and that's the main you can say the time complexity, sorry, the space complexity will be not big O of something, it will be basically n by n, so n square. But here in this case we have a space complexity of n only. So there are two different approaches and you will have to know which approach to use. For example, if you have vertices which where most of the columns or most of the positions are going to be filled with some data, you can use a adjacency matrix. But if you have a matrix with so many zeros, then it is actually recommended to use a list. Such type of matrix is known as a sparse matrix, right, or a sparse array, which I am going to write here. So in this way we can implement the matrices and agency, and in Python we are going to implement this data structure, but we are not going to use any of these two. We are going to use a third approach which I really found very interesting, which is to use dictionaries in Python. So first of all, I have created a dedicated video on dictionaries in Python. You can watch that in the Python playlist or in the Python course, and there you will be able to understand about dictionary. That's basically all for this tutorial. Thanks for watching, and make sure to subscribe our channel and hit the notifications bell so that you will be able to get all the notifications whenever we will launch a new tutorial. So basically we are going to write a program in Python here which will use adjacency list to implement a graph data structure. We will be using these types of implementation of graph in a lot of future coming tutorials where we will be solving problems related to graph theory. So let's start with this. Now the first thing we need to do here is, as we already know that this is actually a linked list, adjacency lists are essentially linked list. Here you can see I have a graph, and here is a representation of the adjacency list. You can see that we have 4 nodes 0, 1, 2, 3, and corresponding to that I have 4 linked lists, and you can see since 0 is connected to 1 and 3, 1 and 3 are in this list. So what we wish to do is we wish to write a program in Python where I will specify the nodes and how they are connected by providing the edges, and what I wish is the program should return the output of all the items in the list, right? So let's start with this now. The first step is very obvious. We will first have to just create a class node, and instead of node let's create a class vertex. Why we are creating this class vertex is because we know that whenever we want to insert any element inside of this list, we will have to first allocate the node. Here in our case the node represents the vertex of the graph, so that's why I'm saying class vertex. Here the first step is obviously to create a constructor using this init constructor, and here I will specify self comma the data of the vertex that we wish to allocate. Now here what I want to do is I want to create a variable with the name, I will name it as vertex is equals to data. And the second thing, we know that this vertex, every vertex that we wish to insert in the linked list will have data and the next pointer. So I am simply going to create a next pointer, and we know that initially it is going to point to null. The second step is to create a class graph, right? Initially this we will have to create the whole graph here. So here also we will have a constructor which is init constructor, and in this init constructor we have self comma the number of vertices that we wish to insert inside of this graph data structure. And here inside of this constructor we will first assign, I will create a variable nv which is basically the number of vertices, and I am going to assign it equals to vertices which was passed at the time of object creation, right? So now let's create the driver program here, which is basically going to, or the driver code which is going to actually run this code. The first thing I need to do is to create an object of this graph class, and here I will pass the number of vertices, right? So let's say the number of vertices is equals to 5 here. So now it will create an object of this graph class with the number of vertices as 5. All right, so here let's first assign the main function. So if name is equals to main function, right? So this is just basically defining a main function, and here I'm going to create the object now. So the main function will automatically run and it will create an object with the number of vertices as 5. The next steps are very simple. We just need to create a function which will basically add the edge to this graph, right? So I will have to add an edge to this graph. So let's take a very first example. When we want to add the edge, we will first provide the source and then we will provide the destination. So here from this example, let's try to construct this graph. So let's pick up a node here. I have picked up this node 0. So the source is here. I'm going to write here that the source is 0 and the edge goes from 0 to 1. So this is one edge inside of the graph. The second edge will be graph dot add edge, right? The second one will be let's say from 1 to 2, right? So similarly we will have such types of construction. So I'm just going to copy this line and I'm just going to paste it here, right? So let's add some more. We have 5 edges here, so I will just write 5 times this one, right? So the second vertex here you can see is 2, 3, right? So 2 is connected to 3 and similarly we have 3 connected to 0 and the final one is 0 is connected to 3. Alright, we have already done that. So 1 is also connected to 3, so we will have to write that also, right? So now we have these 5 edges inside of this graph. This graph is an undirected graph, so I will have to make sure that here when we are trying to add these edges, I should consider that case also. So we will see that in this program only. So here what I am going to do is I am going to create or define a function which is the add edge function, and it will basically add the edge to this graph. This will have a self parameter, the source parameter and the destination parameter, something like this, right? So before moving on to this function, there is one more parameter that I will add to this constructor here, right? This is a very important parameter. I am going to write self dot, I will create a graph array, right? So let's create a graph array here which will be equal to none times self dot nv, right? So what are we trying to do in this line? You can see that we will have to actually create 4 linked lists. For that what I am going to do is I am going to create an array with the 4 positions and initially they are all null, right? So whenever I want to push an element inside of any linked list, I will push that inside of this array, right? So here I have just created that. So nv is the number of vertices which is here, right? So this declaration is something similar to like this, right? So in our case, since we have 4 number of vertices, so it is basically going to create an array with these 4 elements. Now these 4 elements starts from 0, 1, 2 and 3, and now what we can do is we can insert each of these linked list inside of this array, right? So I'm just going to revert it back to what it was originally. We will have to write it like this, right? Now let's move on to the very important function which is the add edge function. So here we will have to write first of all, first thing is very simple, which is we need to first insert the node, right? We will have to allocate the node using this vertex and we will provide it with the data, right? So here we have the vertex and I want to write the source here, right? So what we are trying to do is source, you can see here we are given 0. So we are first going to create a node which will basically be created using this class here, which is vertex. Now this will have the source data. Source is 0 here, you can see that. And here let's first make it destination, not source, right? So first we want to allocate the destination. So you can see for 0 we have 0th position. The first node that I wish to enter is 1, which is the destination, right? So you can see here 1 is the destination. So I will allocate it using this command, which is vertex, right? So after allocating this, I will have to make sure that this node, the next of this point, this particular node, which is 1 in our case, in the first one, if we consider the first edge only. So now I'm going to write two of the very important lines here, right? Make sure to watch this part carefully, because these two lines are the crux of this whole video, right? So the first thing I'm going to do is I will have to reassign the next pointer of this node. So let's see how we can do that. Now first of all, this node 1 is allocated, so this node will have a data 1, and you can see here it will have a next pointer which is pointing to null. Now every time we want to add an edge, what we are trying to do is we will have to allocate the node, and since this array here is going to manage all the linked list, we will have to push these edges or these nodes to this array, right? So we will have to push them here. Now here we know that it will create n number of none places here, which will basically the number of linked lists that we wish to insert here. So what we will simply do is, once we have allocated the destination node, we will assign the next pointer of it to the self.graph array, right? So we have this graph array, and to the source position, right? So you can see that source is 0. So at the 0th position in this array, we are going to make sure that this node is pointing, the next of this node is going to point to that position. So let's see here what will be the status of the array after this first edge is inserted. So instead of writing this, let's assume this, right? Since we have 4 nodes, it is going to look something like this. So you can see here at the source position of the graph array, we have none. The next of node is none. It is going to point to this value here. So we know that this line will actually create a node which has a value 1, right? So let's write it on this line here, because here we are creating a node which has a 1 and it has a null pointer, right? So here in the first edge we are allocating 1, which is also having a next pointer which is pointing to none. Now what I will do is, the next of this pointer node, right, it was pointing to none, I will reinitialize it, or I will reassign it to the source position of this graph array, right? So what is the source position? It is 0. So at this position 0, now it is going to become something like this, right? So now we have inserted node 1 inside of this graph array. Now let's take a look at the second line, which is again a very important line, which is self.graph array. The source position of this is going to be equal to the node, right? So at the 0th position of this graph, right, we are going to make sure that it is equal to node. So this whole node with the data is going to get inserted here, right? So node dot next is actually equal to whatever position we have here. So after this, the status of the array will look something like this. Now if we want to insert the elements, if here we have 0, 1 and we wish to insert 1, 0 edge what I can do is, instead of again making another call of 1 comma 0, if we want to insert 1 comma 0, instead of making another call, we can just copy these 3 lines and just replace the source and destination, and this will automatically work. Now let's write a utility function which is graph.printGraph function, which will print all the values inside of the graph, which will display all of these linked lists. So here I will simply define a function which is the print graph function, right? So the way I'm going to do here is, I'm first going to write a for loop which goes from for I in range, right? It will go from each and every vertex. So in range we have self.nv, which is the number of vertices. So we want to run an iteration so that we can go from each and every edge, from each and every vertex. So we have self.nv. So this function will basically run 4 times, and each and every time I will have to display the whole linked list which is stored inside of this graph array here. So the way to do is, I'm first going to write here that print that list of vertex, right? So I will write some curly brackets here, right? And here I am going to write dot format. Instead of these curly brackets, I want to insert I. So what this will print is list of vertex 0 in the first iteration, then 1, then 2, and then 3, and so on. So first we are printing that list of vertex 0. So these curly brackets is actually formatted as I, and here I am going to also add a separator which is end equals to this, right? Alright, so let's move on to the next line inside of this for loop. What I am going to do is, I am going to create a temporary value and I will assign it to this graph so that we do not mess up with anything related to this graph. So I will create a temporary graph array, and we have the ith position here. So every time I am actually taking each and every position of this graph array, right? So at the first iteration, it will pick up the list or the whole linked list from the 0th position of this array, right? So let's see how we can simply print this, right? I will run a while loop, while temp, and this while loop will keep running, and we will keep assigning temp equals to temp dot next, right? So in the linked list, we are going to actually use this updation value so that the temp will go from the first value in the list and it will go till the end, right? So here we will have to leave some indentation also, and here I am going to print the value, right? Let's print the whole linked list here, like this, and here I will again use the format function, and in the format I am going to write temp dot value of the vertex, right? So we have vertex here, and again I will add a separator which is end equals to 0, right? So end equals to this double quotes. So what I am going to do here is, I am actually displaying the value of the linked list at the temp dot vertex, and I will keep updating the value of temp to the next node, and it will keep displaying until and unless the value of temp becomes null, right? So it is a simple way to traverse in a linked list. We will have to remove these double quotes from here, and now this program will run. And here this print statement, I am going to align it to the while loop only. And now let's just save the changes and let's see the output of this program here in the terminal. Alright, so you can see here, this is the output of this program. So the list of vertex at 0 is starting from 3 and 1. So This is right because 0 is connected to 3 and also 1, and similarly for vertex 1, 3 2 0. For vertex 2 we have 3 1, and for vertex 3 we have 0 2 and 1. Now we are going to cover traversal in a graph data structure. The first technique to do traversal or search in a graph data structure is the best, which is the breadth first search. And breadth first search is very important. It has a lot of applications, and in a lot of interviews there are a lot of questions that come from this particular algorithm. So we will write the algorithm in Python. So first of all, we have a given graph data structure here, which is has these vertices, and this is how it is connected. So we have 0 1 2 3 and 4. So the first thing I'm going to do is, in this program I'm going to actually, and here I will write the main function using name equals to. Here I will first create a graph representation of the corresponding graph that I have drawn here. The first way is to use the matrix, the second is to use the adjacency list, but here we have an interesting option, which is the third option, which is to create a dictionary, right? So here we are actually trying to create a dictionary here. So I will just write that we are going to create a dictionary to represent this graph. So in dictionary we have keys, and separated by colon we have values. So it's something looks like this, right? So basically we are going to write the keys as the vertices. So 0 is a vertex, and then we have 1 as the vertex, and then we have 2 as the vertex, then 3, and then 4. And now what I'm going to do here is, in the values I'm going to provide an array. In this array we will actually put all the elements that are directly connected to this node. So if we consider 0, 1 is connected, 2 is connected, and 3 is connected to it. In case of 1, we have a 0 connected to it, and then we have 2 connected to it. And now let's consider node number 2. It has 0 connected to it and 1 connected to it. And the final one is 3. And here 3 is connected to only 0. And the last one is 4. It is connected to 2. So here we have a representation of this graph. We will leave some indentation here. So now what I will do is, I will make a call to a BFS function here. And here I will supply it with two values, graph, which is this dictionary, and also the node from where I wish to start the traversal, right? So 0 is the node from where I want to do the traversal. So let's understand what exactly is breadth first search now before implementing this function, and let's see what is the approach in the algorithm. So here we are going to start from this root node. So I'm going to write here that this is the starting position. The basic idea of breadth first search is to traverse, or is to display all the adjacent nodes to it, right? So if we are going to start the traversal from 0, the BFS algorithm is going to move the traversal in such a way. So we will first print 0. 1 is directly connected to 0, you can see that. 2 is also directly connected to it, and 3 is also directly connected to it. So first we will display 1, then we will display 2. Now when we reach 2, we can see that 4 is connected to 2, but we are not going to display it because this is the main rule of breadth first search, that we are going to first go to the breadth and then only we are going to increase the levels. The next one we will have to display 3, and now we are going to display the values of the neighbors of these, which is 1, 2 and 3. So 1 has a neighbor 0 and 2. Both are already being traversed. So once we have done traversal on a node, we are not going to visit it again. Similarly with 3 also, 0 is already visited, but 4 is not visited. So now I will insert 4 here, right? So it is known as breadth first search because if you consider a tree, a data structure like tree, and we apply the same rule, which is to display all the adjacent nodes. So if I will try from the root node, we have these two adjacent nodes. So basically we are actually trying to traverse level by level. So that's why it is known as breadth by breadth, right? So this is a breadth first. In depth first, we are going to explore in the depth, right? So if I go from this node to this node, I can ignore these nodes. I will first explore this node to the whole extent, right? So that's how the DFS and BFS works, right? So now let's see how we can implement this in Python. So first thing is we are going to create a visited array, right? We can use the set function to create such type of an array, and initially this array is empty. This visited array is going to be the final output where we will display all these all the nodes which we have traversed. The second thing is we are going to use a queue data structure. Queues are basically used to perform BFS algorithm because it is actually a very feasible data structure in this type of scenario. So initially the queue will hold only one element, which is 0, which is the root element, right? So we will first add 0 to the queue. So first of all, let's implement this part in the in our Python file. So the first thing I'm going to do here is I'm going to define a function BFS. It will take the graph and it will take the root element, and in the next line I'm just going to write I'm going to create a visited array using set function, and then I'm going to simply create a queue data structure, right? Now here we can actually create a queue using list. In Python we can create an empty queue, and we want the first element, root element, should be there, so we can do it something like this. This is not an ideal way. We will use the collections library because when we want to perform frequent NQ and DQ operation inside of a queue, this is not a recommended way. Although this will also work, but still we are going to make use of the collections library here. So I will just use collections.dq function. Dq function is actually used to create a queue, and here it will create an empty queue, but I want the root element to be inside this queue, so I will just write root here. This will create a queue with a root element. Here in our case it is 0. Now in the next line, let's see what we will do next after inserting 0. The next thing is, here we know that this is a queue data structure, so it has two positions, which is the front and the rear position. We perform the NQ operation at the rear position, and we perform the DQ operation at the front position. So the first thing I'm going to do here is when we insert any element in a queue, we are going to DQ out of it, right? So we will pop this element out of this queue, and whenever we pop an element out of a queue, we are going to insert it in our visited array, because now we are going to visit this array, right? So let's implement this part first. So here what I'm going to do is first of all I will create a while loop which will go till the queue is empty, right? So the algorithm will start from the first one, and until and unless this queue becomes empty, it is going to perform the operations, which is the first one is to perform the DQ operation, right? So what I'm going to do here is I'm going to write queue.popLeft function, right? So queue.popLeft function, it is going to DQ the element from the left part. One important thing is here we will have to import the collections library, and here we are actually popping this element out. Now since we will have to store this element in the visited array, I'm going to create a vertex variable which will hold this element, and I'm just going to quickly add it to our visited array using add function, and here I will just write the vertex, right? So now we have added the vertex. Now let's see what is the next part. The next part says once you have DQ'd an element out of the queue, it means that you are visiting that particular node. So what you have to do is you will have to find all the adjacent nodes to this queue. So you can see 1, 2 and 3, these are the adjacent nodes, and you will have to push all of these nodes inside of the queue. So I will push 1, I will push 2, I will push 3 here inside of the queue. We'll have to do the NQ operation. And one more thing which is very important condition here, which says that whenever we are performing the NQ operation, right, whenever we are trying to NQ all the adjacent nodes, we are going to make sure that they are not already inside of our visited array. So you can see here 1, 2 and 3 are the adjacent nodes, but they are not in the visited array.
so I'm going to push all of them here. In the next iteration, I will pop the element 1, I will mark it as visited, and now you can see 1 is directly connected to 0 and 2, but 0 is already there in the visited array. We will write a condition for it, and 2 is not is not here, so we can enqueue 2 here, something like this, right? And now what the algorithm will do is, now we will dequeue 2. So 2 is being dequeued, so it will also be marked in the visited array. 2 is connected to 0 and 4. 0 is already there, but 4 is not there, so we will enqueue 4. Then we have this 3 here, so we will have to see 3 is not there in this list, so I'm going to enqueue 3 here, right? So first of all, I will dequeue 3 and mark it here, right? So 3 is connected to 0, so this 3 will not come here, right? We are dequeuing 3. So once 3 is dequeued, it will be marked here. 3 is connected to 0. 0 is already there in our visited array, and now the last one is 4. So 2 will be dequeued, right? When we are dequeuing it, we will check. You can see that it is already there in our visited array, so we are not going to push it in the visited array. We are going to move to the next element. So now 4 will be popped out, and since it is not in the visited element, we are going to push it in this visited set, and the final result is here, and we are just going to display this final result, right? So let's write the very simple algorithm here. What I want to do is, at each and every iteration, I will have to first get all the adjacent nodes. The way to do is, if I want the adjacent nodes, which is the list of all the nodes at the vertex position, right? So vertex is actually the element that is popped out, which you can see here, and here this vertex initially was 0, so you can see it will give me this list 1 2 3. So the value of I will be 1 2 and then 3. So at each and every iteration, I will check whether the value I which I want to insert or enqueue inside the queue, whether it is already there inside the visited array or not. So I'm going to write here, if I is not in a visited array, now I can perform the queue operation, enqueue operation, using the append function. I'll just write I, right? So now this will append the ith element in the queue. This will go on again and again until and unless the queue becomes empty. So after 4, the queue will be empty because all the items has been dequeued out of it. Now we are going to display the final result here. So here I'm just going to print the visited array here. The node 2 is connected to 0, 1, and it is also connected to 4. So here I just forgot that. So I will save the changes and run this program. Right, so now you can see here it will display the output 0, 1, 2, and 3 and 4.
We are going to study the DFS, which is the depth first search algorithm in graph data structure. We have previously covered the breadth first search, and we have also implemented it in Python, and here we are going to do the same. And basically there are two approaches to implement the depth first search. The first approach is the recursive approach, and the second approach is using the stack data structure. In this video we are going to focus on the recursive part only. So here you can see I have a graph data structure A, B, C, D, E, and here you can see I have used a similar representation of this graph using a dictionary data structure. So here we have graph equals to, and you can see this is a dictionary with keys and values. Now value is a whole set of all the adjacent nodes which are connected. So here you can see if I have a key which is A node, so A is connected to B, C and D, so they are the values of this key. So you can see here A is connected to B, C and D. Now B is connected to A and E. Now B is connected to A is already covered here, so we are not going to rewrite it here. So B is E is the adjacent node of B, so that's the representation of it. Now we have finally C, D and E in similar way. You can see D is connected to A and C, and we have already covered that before, because you can see that C is connected to D and D is connected to C is same, so we are not going to rewrite it. So D, the adjacent node of D is C, but we are not going to write C here because it's already covered here. and that is the same case with E also, right? So let's first understand what is the core understanding of the DFS algorithm, right? So the first thing is in DFS, before starting with the directly with this graph data structure, first let's understand how it works in a binary tree, right? So I'm just going to draw a very simple binary tree here, which has all of these nodes, and we know that in traversal or in search we're going to visit a node only once. This is the root node, right? And I want to start the traversal from the root node. In the graph data structure also, we will start with the node, which we will also call as the starting node or the root node. Now in the DFS data structure, which is DFS algorithm, we do is from root node, you can see I have basically two positions, right? I can go to the left part or the right part. So let's say I will move to the left part of the tree, right? So this is the left part. So now in the left part, if I move to this node here, so I'm visiting it here. Now instead of visiting the adjacent node, which is here, I'm not going to visit it because they are at the same level, or we can say that they are at the same breadth. And since we are not concerned about breadth, we are concerned about depth first. So instead of visiting the second node, we are going to explore this node first, right? So now after visiting from here to here, we are now going to visit this node. Now here we have this node also. We are not going to visit it now because we have to first explore to the depth, right? So the idea of DFS is to explore the depth. Now once we have explored the full depth, there is nothing else remaining here. What we can do is we can use backtrack, right? So a recursive approach, what will do is it will keep calling the DFS function to the next node again and again, and once we have reached the end of the whole data structure, or you can see the leaf node, we can do is the algorithm will backtrack to the previous node, and then it's time to visit the other nodes as well. So now it will visit this node, and similarly all of these nodes will be visited in the same fashion. So let's understand DFS more clearly in this graph data structure. We are going to start with A. Directly connected nodes or the neighboring nodes of A is B, C and D. Now let's choose one from this. Let's choose B first. So first I will visit A, which is the root node. The second is going to be B, right? So we are connected to B. Now A is connected to C and D, but we are not going to visit C and D because they are the neighboring nodes. So because we are not doing the breadth first, so we are not going to explore them. We will have to now explore B and to go inside the depth of this B, right? So B is connected to E and A. A is already visited, we are not going to revisit it, right? Now we have E here, we are going to visit E. Now after we have visited E, we are now going to visit C, and now C has A, D and E as the directly connected nodes, right? A and D, A is already been visited, D is not visited, E is visited, so I'm going to now finally visit D. So that's how a depth first search works. It goes into the depth of the data structure, which means it is going to ignore the adjacent nodes and it will keep exploring only one node at a time. That's the basic idea of DFS algorithm. Let's now implement the recursive approach, which we will use in this tutorial, right? So recursive approach is basically a function calling itself. So let's implement it in Python here. Now you can see here we have created a visited set, right, which is basically an array which will contain and hold all the elements or the nodes which we have already visited. Here you can see I have just made a call to a DFS function and I have passed it the visited array, the graph data, the whole graph structure, which is dictionary in our case, and the node from where we wish to start the traversal or the search. Now here we have the function call itself. This is just define DFS. We have visited array, graph and the root, which initially will be A, right? Now what we will have to do is, the idea is, the first thing we are going to do is we are going to start with A. A is not there in the visited node, right? So the first thing we need to do is, whenever we want to do a traversal in depth first, we first need to check whether the root is inside of the visited set or not, right? So I will write if root not in visited, right? So A was not in visited, so the next thing we are going to do is to print the node which we are actually now visiting inside of this if case, and we will also insert it inside the visited also, right? So first we will print the root element, which is A, and then I am going to simply add it to the visited array using visited.add function. Now root will be added to visited, so A is now there inside of the visited array. Now what I will do is I will have to explore the adjacent nodes, which is B, C and D, right? So I will write a for loop which will go from inside of the key. So here you can see for neighbor in graph root, right? So what graph root represents here, we have already seen that similar thing in DFS also. Graph root means that we are actually fetching the values of this key root, right? So if I will pass A here, we are going to get this whole set B, C, D here. So the neighbor will go from B, then in the next iteration it will be C, and then in the next iteration it will be D, right? Something like that. Now what we need to do here, the next step is to make a recursive call. Now in the recursive call, we are going to recall this function, which is DFS function. We will pass the same visited array, but now the visited array is now changed. It has A inside it, and then we will pass the whole dictionary, which is the graph, and instead here we will pass the first neighbor. So in the first iteration, the first neighbor is B. So now we are actually calling this function again using this neighbor B, right? So this neighbor B will call this function again. It will search it inside the visited array. It's not there, so now it will add it to the visited array, and we will also print that. And now again we will you can see now this in the first iteration, it will again check the neighboring nodes of the B node, right, which is E. So now it will again make a call to this DFS function. The neighbor will be E, and it will do again and again until and unless this for loop in the very initial iteration, when it will cover all the iterations, which is basically covering A node, B node, C node, D node and E node. When it will be able to run all of this, it is now going to backtrack and it will visit all the remaining nodes as we have seen inside of this, right? So this is basic working of this whole algorithm. In recursive approach, it's simple because what we are doing is, whenever we are visiting a neighboring node, right, at each and every iteration I am visiting a neighboring node, but instead of actually covering the adjacent nodes of the neighboring nodes, what I am trying to do is I am making another recursive call. What it will do is it will restart the whole algorithm from this BF node, right? So first we want to run the algorithm for A, visit the B node, and I'm going to do similar thing with B, right? That's why we require recursion, because we are doing the same task again and again. So in B, when we will visit B, we'll have to perform the same thing, right? Search for the neighboring nodes, which is A and E, right? Again we will search whether it is there in the visited array, and we will print it and we will add it, and then we will visit E, then C and D, right? So that's how this whole algorithm works. Now let's run this algorithm and let's see what is the output here. So I will quickly open the terminal here, and here I will just write python 3 dfs.py, and now you can see here the output is A, B, E, C, D, right? So make sure to run this program by yourself and make sure to understand how this recursion is working, and if there are any doubts you can ask it in the comments. Make sure to like this video, subscribe our channel, and in the next video we will cover the array part, the stack part of the DFS. By using stack data structure we can also implement DFS, and we will also see what are the time complexity advantages and disadvantages in using these two different approaches, because it may come inside of some interview.
We are going to study the Dijkstra's algorithm in Python, which is to find the shortest path when you are given a graph data structure. So we have already covered graph data structure and algorithms like the DFS and the BFS algorithms. Now this tutorial is very important for all the beginners who are really interested in a lot of competitive programming problems, because in this single problem we are going to cover a lot of important things. This algorithm uses greedy approach, so we will also learn that, and I will also share some of the interview tips that will help you understand where the optimizations in an algorithm can be done, and an algorithm can be made optimized by the time complexity, right? So let's start with the algorithm. Here we are given this graph data structure. These are the nodes A, B, C, D, E, F. These nodes have, you can see, edges which are actually weighted edges, means that they have some distance in between them. And you can see I have this A node as the starting node, and I am assuming that F node is the destination node. So here the source is A and destination is F. So what the interviewer will ask you, the problem that this algorithm will solve is to find the shortest path from the starting node to the terminal node. So here we want to find out the shortest path and the shortest distance from A node to the F node, right? So let's see how Dijkstra's algorithm can be used to do so, right? So the idea of Dijkstra's algorithm is very simple. What we are going to do is, first let's start with the explanation part. So here we are going to start with the 8th node, which is assigned a cost of 0, because it actually you can see this is actually the cost. So for each and every node we are going to assign a cost, and we will see what is the significance of that cost. So A has a cost 0, which means it actually cost nothing to reach 0, because it is actually the starting node. And then you can see that except A, every node has an infinite cost. You can see they have this infinite cost, and which means that we have not yet explored the cost of reaching from the starting node to that node. We don't know the cost at this point. So we just assigned it the maximum value, which is infinite, and we know that we can achieve this in Python using the sys library, and we have the max size function which can actually give us the maximum infinite value, right? So let's see how the algorithm will proceed. So we have the F node as the terminal node. So here I am going to write that this is going to be the terminal node. Alright, so the first thing is we need to find out the neighbors of the first node. We are going to start with the 8th node. A node has two neighbors, which is B and C. The first thing I'm going to do is once we have the adjacent nodes, right? So I'm going to write step 1 here, which is to find the adjacent nodes, and we know that adjacent nodes of A is actually B comma C. And obviously we can use a dictionary to find that out also. We will see that in Python also. So adjacent nodes are B and C, and what I'm going to do is I'm going to find out the cost of B and cost of C, right? So once we have find out the neighbors of A, we are going to find the cost of each neighbor, right? And the cost of each neighbor is actually going to be the cost. So here we have, let's say we want to calculate the cost of B, and B is actually the it's not just the cost of B, it's actually the cost from going to A, from A to B, right? So if I want to go from A to B, what I can do is I will have to first see that actually B is a neighbor of A. So first we will have to use the cost of A, right? What is the cost of reaching to A? And we are then going to add the distance from the node A to the node B, right? So cost of A, initially we have assigned it 0, and so here we are at 0, and the distance from A to B is 2. So cost of B is now going to be 2, right? So now what I can do is instead of maximum infinite, I am going to assign it as a cost of 2, and similar thing we are going to calculate the cost of C, right? The cost of C is actually from the 8th node to the C node, so 0 plus 4 will give us 4. So I can simply do this, right? So that's the idea of Dijkstra's algorithm. We are actually going to use this cost to find which node to explore, right? So out of these two neighbors, which is the third step, right, find the minimum cost neighbor, right? This is the step number 3, a very important step. And here so we have B and C. Out of these two, you can see B has a lower cost, which is 2. So minimum cost neighbor out of 2 comma 4 is actually going to be 2, which belongs to the node B, right? So now we are going to ignore C, and now we are going to explore the node B. And so we know that at this point we have the neighbors of again we are going to follow these steps, right? So now for B, I'm going to write here, for B we are going to first calculate the neighbors. So for B we have the neighbors D and C. Okay, so we have these two neighbors, and A is also the neighbor, but remember, once we have calculated the minimum cost neighbor, we are going to add another step 4 here, which is mark the node A as visited, right? So we are actually going to maintain a set visited, which will initially be empty set, but now we will add a node to this visited array. Now once we have added it, we are not going to consider it as a neighbor of B, because we have already calculated the cost for that. So now these two D and C are the neighbors of B, right? So now we need to move to the step number 2, which is to find the cost of C and cost of D, right? So cost of C is calculated as cost of B plus distance from B to C, right? A very simple formula. So cost of C is equals to cost of B plus distance of this, and now you can see that cost of B is actually 2. So I'm going to write here 2 plus distance from B to C is actually 3. So this will give me a result 5, right? So cost of C is going to be 5. Now you can see here that C already had a value of 4, and this value which we have calculated now is 5, and we can see that here we need to do actually a comparison, right? So 5, which we have calculated the cost, is greater than 4, so we are not going to assign it the value, right? So I'm just going to write here not assigned. The reason we are doing this is because when we are actually calculating this cost is actually the cost of B, which actually takes a path from A to B, and that's why we got the cost 2, and from B to C we have 3, right? So the cost is 5. So this comparison basically says that instead of choosing the path from A to B to C, which is actually 5, we are not going to reassign this value of 4 to 5. We are actually going to keep this value 4, which means that A to C is actually lesser, so that's why we will not assign it, right? So this comparison is also very important, and we will do that here also. If you can see here, A has a distance of 2 from B, so infinite value is actually greater than 2. So whenever we get a value lesser than the cost assigned to any particular node, we can reassign it, right? So that's the basic criteria of assignment, right? So I'm going to write here that this comparison is basically used to do the assign work, right? So now we have assigned this. You can see 5 is greater than 4, so we are going to keep the value of C. Now let's move on to the D. You can see the cost of D will be 2 plus 8, which is 10. 10 is you can see 10 is less than infinite, right? And this is actually for the node D. So since 10 is less than infinite, we are going to assign the cost 10 here, right? Because that's the comparison criteria which we will write in the algorithm. And now what we will do is, out of these two neighbors, we will have to find out, which is step number 4, which we have to do is find out the minimum cost neighbor, right? So out of C and D, you can see that the minimum cost is C, right? It has a value of 4. 4 is less than 10. So now what I'm going to do is, the fifth step is to insert the element inside of the visited array. So now visited array already had A, and now we are going to append B to this visited array. And now we have the C and D. So now we are going to visit C. So for C, right now I'm going to write for C. I'm again going to follow the same steps. So now instead of writing these steps again, I'm just going to follow the steps. So for C, I have these neighbors, which is A, B, D and E. A and B are already in visited array, so I'm not going to visit them. D and E are not in the visited array. So now what I will do is, I will calculate the cost for D first. So the cost will be 4 plus 2, which is 6. And you can see 6 is less than the cost of the node D, right? For that, I can just write 10 is greater than 6. So what I will do is, I will assign this 10 as a value of 6, because that was our criteria of assigning, right? Which you can see here. So now this D node has 6, and it basically means that 6 is actually the distance from A to D, right? You can see if I go from A to C, the distance is 4, and from C to D, the distance is 2. So it is 6, right? So this 6 represents that the path taken is from A to C, right? And now we will do the same step for E. For E, we have C is 4 and this distance is 5. So 4 plus 5 is 9. 9 will be assigned because it is less than infinite. And now we are actually going to mark C in the visited array. So C will also come here. And now out of D and E, which one is less? You can see D is less. So D will be now evaluated. For D, we have these two neighbors E and F. And from here, 6 plus 22. You can see the value is 28, which is less than this. So I will assign it here. And from D to E, you can see I have a distance of 6 plus 11, right? So 6 plus 11 is 17, and since 17 is greater than 9, I'm not going to reassign it, right? So I'm going to leave it as it is, and now this D will be moved to the visited array again. Now we will have to find out which one of them is minimum. You can see this E is minimum, so I'm going to evaluate E now. So E has only one neighbor, which is F. The cost will be 9 plus 1, which is 10, right? And 10 is less than 28, so we are going to reassign the value of F to 10. So the value, this is the terminal. Now we have reached the terminal, and the cost at the terminal is 10, which says that that the path taken was from E to F, and E has a cost of 9, which we have got by moving from path E to C to E, right? So A to C is 4, C to E is 5, which is 9, and 9 plus 1 10, and you can see this is actually the shortest path, right? So that's how this Dijkstra's algorithm works, by considering the cost, and comparison is important here. We are going to assign the cost only when the comparison condition is true, and then we are going to find the minimum cost neighbor. Now at this point, you can see in this algorithm, the step number 4 is very important, which is to find the minimum cost neighbor. And at this point, the interviewer can ask you, what is the algorithm you are going to use to find the minimum cost neighbor out of all the neighbors, right? A lot of people can actually use some sorting algorithm. So what you can do is, the idea is to sort all the cost of the neighbors, and then you can just pop out the first element. And for that you will have some time complexity, but there is one more important and a better time complexity wise algorithm which we can use is minimum min heap, right? Or we can say min priority queue, right? So at this point we can optimize this algorithm, which is the Dijkstra's algorithm, and it is a very important step that we use a min priority queue instead of some other comparison and iteration things, because that is going to increase the cost, increase the time complexity of this Dijkstra's algorithm. So here we are going to at step 4 we are going to do the optimization. So basically Dijkstra's algorithm has a lot of application, and you can see from A to F if I want to send a packet. So in networking it has a lot of applications. So if I want to send a packet from A to F and I want to find out what is the minimum path that I can have, I can actually use this algorithm. The second thing that we also need to do in this algorithm is to also find the path, right? We also want to find the path which is the shortest path, right? So we have already find out the shortest distance by using this comparison of cost and calculating the cost. Now the second thing is to find the shortest path from A to F. So the basic idea algorithmically which we can do is using cost we can also use and maintain another variable which is the predecessors variable, and predecessor is basically a set which will be empty for all of these nodes. And what we are going to do is whenever we assign whenever we do a comparison, we are just going to append the predecessors inside of this set, and for each and every node we will have a set of predecessors of from the starting point A, and this way we can actually get the shortest path, right? So this part will become more clear when we will see and take a look at the algorithm. So let's take a look at the Python program here. So here we have a Python program. You can see this is actually the main function, and this is actually a graph which I have graph representation in the form of a dictionary. So this algorithm that I am going to show here is you will not be able to find this anywhere because I have written it, and it is really very easy to understand. So make sure to watch this video till the end because it is a very important algorithm, and if you will learn this algorithm it will help you a lot, right? So first of all, one important thing which I missed here is that here at step 4, which is finding the minimum cost neighbor, which we are doing at each and every step, is actually known as a greedy approach, right? So this is known as a greedy approach because at each and every step we are choosing a node greedily, right? Our greed is actually to basically find the minimum value. So I'm just going to write here, our greed is to find the minimum distance. Minimum cost is actually basically the minimum distance from the starting node. So at each and every step we are becoming greedy that we are going to find the minimum cost out of all the neighbors, right? So that's one important thing about this algorithm. It uses greedy approach. All right, so now let's move here. So here we have the graph representation in the form of dictionary, and here we have all the nodes A, B, C, D, E, F, and this is a dictionary of dictionaries. Now you can see A is the key and value is the whole dictionary itself. Now A is connected to B and the distance is 2. A is connected to C and the distance is 4. And similarly for B also we have done the same thing. B is connected to A with a distance of 2, and C with a distance of 3, and D with a distance of 8. Similarly I have done this for all of these nodes, right? So then we have a variable known as source, which is A, which is the starting node. Then we have a destination, which is the ending node. And now we have, I've just made a function call to this Djikstra function by passing these three variables, which is the graph, this whole dictionary, the source, and the destination, right? So now let's write this, now let's implement this function. Before implementing this function, make sure to import the sys library, which is used to actually assign the infinite cost to all the elements except the starting node. And then we have from heap queue, which is actually a library which will be able to help us quickly implement the heapify function and heap push and heap pop functions. So these are some utility functions. Alright, so now let's move on to the Djikstra function. The first thing I need to do is to create a infinite value, right? So here what I can simply do is I am going to initialize a value here, which is going to be INF, and this INF value is equal to the sys.maxSize. Max size is it will return the infinite value, right? The maximum value that it can hold. Now we have this infinite value. Now what I'm going to do is I'm going to create a dictionary with a name node data. So each and every node will have a data and it is actually a dictionary. So here you can see for a node we have a dictionary of dictionary. So a will have two variables, one is the cost and the second one is the predecessors. The cost is initialized as infinite and the predecessor set is empty. I'm going to do the same thing with the node B, C, D, E and F, right? So this is actually a dictionary of dictionaries. So each and every node here inside of this graph will have a cost and a set of predecessors. So the predecessors will actually give me the path from the 8th node, which is the starting node, to that node, right? So now what I'm going to do is I will have to make sure that whatever the starting node is or whatever the source node is, I will have to assign the cost of that node as 0, right? So in case of A, I will have to assign this cost of INF to 0. For that I will write this line, which is node data source. Source is going to point to A here because we have passed A here, you can see. So here the cost of this node will be reassigned to 0, right? So INF will change to 0. Now we are going to create a set of visited elements. Initially it will be empty. And now I'm maintaining a temporary variable of the source. So what I will just do is I will keep reassigning this temporary variable, which is the source variable, to the element which is minimum out of all the neighbors, right? So that we can actually proceed the same algorithm, the same steps by actually just changing the temporary pointer, right? So initially it will be pointing to the source, which is A in our case, and then out of B and C you can see minimum is B. So we are going to reassign the temporary variable to this minimum element of the heap, right? Alright, so now we have to create a for loop which runs from I in range 5. The reason why I have written 5 here is that this is going to be completed in 5 steps, which is n minus 1 steps, where n represents the number of vertices, right? So here we have 6 vertices, so I've written here range 5. So it will run 5 times. Now let's move on to the next step. The next step, which is a crucial step, is to find out whether the temporary variable or whether the source is in the visited array or not. So every time we are going to run a loop, we will have to check whether it is there inside of the visited array or not. Right now, if it is not in the visited array, I'm just going to push it inside of the visited array by using visited.append temp, right? So I'm going to append this temporary variable because we are now visiting this variable, visiting this node, which is the temporary node, and when we will visit B, C and other elements according to whichever has the minimum cost, I'm just going to append it inside of the visited array. Now the next step is to create a min heap. This min heap is actually an empty set. Now what I will do is I will create another loop which is actually used to traverse inside of the neighbors of this temp, which is the source, right? So the source initially is A, and if I want to find out the neighbors of A, I can actually do that by writing this loop for j in graph temp, right? So graph is actually this whole dictionary. Temp is the source, which you can see A is going to be the first one. So A has these two neighbors B and C, right? So now what this will do is this loop will go from the all the nodes inside of this dictionary which is pointing to this temporary variable a. So the value of j will be b and then it will be c, and when we will reassign this value of temp according to the minimum cost neighbor, then it will be b, and again the value of j will be a, c and d, right? So the reason why we are writing this for loop is to actually find out which one of the neighbors have a minimum cost, right? So here I am going to actually first see whether the neighbor is already in the visited array or not, because we know that if the neighbor is in the visited array, we are not going to calculate the cost of it, right? Then we are going to write this very important step here. So first of all, I will just move it here and let me just resize it. Okay, so here you can see this important step. This step calculates the cost of the neighbor, right? So now let's see how we can do that. Here you can see we have node data. Temp is actually the node which we are currently visiting. So we will see what is the cost of that, right? So if I'm visiting a, I will first calculate the cost of it. So in the formula here, which you can see, I have already written here, first we will have to calculate the cost of a. So a in our case is actually the temporary variable which is actually pointing to the variable or to the node which we are currently visiting. And then we are going to add it with the distance from a to b. We can get the distance from the this a to b by using the graph dictionary here, right? So here you can see I have first calculated the cost of the temporary variable which we are visiting. In the first iteration it is a, so it is this whole thing will be 0, right? And then it will be something else, and now we have to calculate the distance. The way to do that is use graph temp j, right? So graph dictionary temporary variable is actually a, so we are here. Now j is actually going to be the neighbor, right? So in the first case the neighbor is b and the distance is 2, so this whole thing here in this expression will be replaced by 2. So 2 plus 0 will be 0, so the cost is 0 here. Now as you can see that this is a for loop, it will calculate the cost of c also. So the cost of c is actually the distance of the temp to the jth position, right, from a to c is actually 4, and the cost of a is actually 0. So 0 plus 4 is 4, right? So 0 plus 4 will give the cost 4. And now what we will have to do is we will have to assign the cost, but remember before assignment we will have to do the comparison, which I have already mentioned here. You can see we will have to compare the values also. So let's see what we are actually going to compare. We will have to compare this cost that I have calculated with the cost which was already existing inside of this node data, right? So here you can see I am actually writing this condition that if the cost that is the newly cost we have calculated here, if it is less than the cost of the neighbor, which is j, you can see it will be b and c. So I will check the cost of these two neighbors and I will make an assignment only when this cost is less than the cost of the neighbor, right? So here you can see I have done this assignment. So this node j cost means that the cost of neighbor, right? So j is actually neighbor. So b will be assigned a cost of 2 and c will be assigned a cost of 4 after the first iteration, right? Now let's move on to the next step, which is to calculate the predecessors, and predecessors will actually give us the list of all the neighbors which we have calculated the cost of, right? So it is actually the path. So node j comma predecessor basically means the predecessors of j, right? Predecessors of b and c. J is neighbor, so we are actually calculating the predecessors of this. So we are going to assign the predecessors only if this condition evaluates to be true, right? So if the cost is less than the cost of the neighbor, then only we are going to assign the predecessors, and the predecessors will be assigned in this fashion. we will first we will first find out what are the predecessors of the node that we are visiting, which is the temp node. So A initially has no predecessors, so then we will add it with the list of the list of temp, right? Temp is actually just the node which we are visiting, so it will convert it inside in a list form, and then only we will be able to concatenate these two lists. So list of temp is actually A in the first iteration, and A will be appended to this empty list, and B here, which you can see is the neighbor. After this assignment, B will have a predecessor of A inside it, right? So when we will move on to other neighbors, we are going to again see the cost, and we are going to append the predecessors of the temporary node with the actual node where we are at, right, which is the temporary node. We are going to push it inside of the predecessors. Now let's move on to the next step, which is to create a heap, right, which is a very important step. So for each of the neighbors, I'm just going to push it inside of this min heap. So here I'm using the heap push function. What we need to do is we will pass it the min heap. Initially it is empty, right? Then I'm going to pass it two values. The first value is going to be the cost of the neighbor, right? So we are actually pushing the cost of each and every neighbor inside of this for loop. You can see we are visiting the neighbors B and C, so I am appending the cost of B and cost of C inside of this heap by using this heap push function. And what it does is, by default, it is going to actually create a min heap, right? So node data will have this. J is actually the neighbor, right? So we will have the two details. First of all, after this heap push function will push the cost of the neighbor, it is also going to push the neighbor, which is J, right? So the heap will look like this after this iterations. You can see we have B and the C node. So the cost is 2 and 4. So 2 and 4 will be pushed inside of the heap, and they will also have this J variable, which is B and C, right? So you can print this min heap at this next step to find out how this heap will look like. Now to find out the minimum element, we will first have to heapify this min heap, right? So we have pushed this all the neighbors with the cost, right? So this is the cost and J is the neighbor. So I have pushed these two data inside of this min heap, and now I am using the heapify function, and by default this heapify function is going to create a min heap, right? So that's an important point. Now what we are going to do is, now we have got the min heap. Now the 0 comma the 0th position will actually give you the minimum element of this min heap, and the 1 is actually going to represent the second variable, which is here. So this 0th variable is actually the cost. So here we will get the cost, but we do not want the cost, we actually want to do a reassignment. So we will have to reassign the temp to the minimum cost. So minimum cost out of B and C is actually B. So this will have we want to give this J variable here, right? We want to actually assign temp equals to B, right, not the cost, so that we can actually proceed with the algorithm in such a manner that it can check whether it is inside the visited array or not, right? For that, what we can do is we will first write min heap 0 and 1, right? So 1 will give me the neighbor, which is J, right? So after the first iteration, when we have calculated the minimum element out of B and C, this statement will assign the value of temp equals to B, right? So 0 is the minimum element and 1 represents the neighbor, which is J, right? Now let's move on to the next step, which is basically just printing out the shortest distance, and the shortest distance is going to be the distance, the cost at the destination position. So you can see the cost at the destination position will give me the shortest distance, and similarly the predecessors will give me the shortest path. So here you can see I'm just converting it to the string, because here you can see we have destination and I will just use the predecessors. Now remember that it will just give me the predecessors which comes before the element before the last element. So I'm just going to append the last element inside of this answer here, which is list of destination, and now this will give me destination path and the shortest distance. Alright, so I'm going to write Python 3. The name of the file is Djikstra, and you can see here we get the shortest distance 10, and the path is A, C, E and F, which is the correct answer. So A, C, E, F is the shortest path, and the distance is 5 plus 4 plus 1, which is 10. So in this way you can see we have got this output. Find union is one such algorithm which is really important because it will be useful in finding and detecting the cycle inside of an undirected graph. So I'm going to write a Python program also to use this find union algorithm to implement the detection of the cycles in undirected graph. And find union is also used in a variety of competitive programming problems and interviews also. So make sure to watch this video till the end because this is really very important tutorial. So before starting with the find union algorithm, we will first have to understand about disjoint sets, which is basically you can consider it as a data structure that we are covering here inside this tutorial. So just consider this set we are given, and let's assume that this set initially has 5 elements, or let's consider it has 6 elements from 0 to 5. Now what I want to do is, let's say I want to actually achieve the partitioning inside of this set, or I want to create the subsets inside this set, right? So let's say I want subsets which is 0, and I want another subset which is 1, 2, 3, and I want another subset which is 4, 5. So whenever in any type of problem where we want to partition a given subset, a given set into a given subsets, we will use the find union algorithm to actually form this type of data structure. And it is also useful in scenarios when we are actually talking about a relationship between some data elements inside of the given set, right? So here you can see that 1, 2 and 3 are closely related, so we have put them in a single set and we are actually calling it as a subset. To achieve this type of a data structure, we will use the find union algorithm, and as this whole algo, as the name suggests, it will consider two very important operations. The first one is the find operation or the find function. What it does is it returns the parent of the subset the element belongs to, right? So let's suppose I want to find out whether an element belongs to which subset. So let's assume that these three sets, or you can say that these three subsets here, they have we have assigned, and we are going to assign one element out of each of them as the parent element which will represent the set, right? So since you can see in the first one we have only one element, so this one is going to be the parent element, and here we have 1, 2, 3 in this subset. So let's assume that we are going to assign 3 as the parent, right? So this arrow represents the parent inside of this subset, and let's assume in case of this 4 is the parent, right? So if I want to find out, right, so if I will execute the function find, or we can also write it as a find parent function, and let's say I will call find parent 2, right? So if I will give it the value 2, it is going to find out the parent of the subset where this element actually belongs, right? So you can see that it belongs to this subset, and the parent of this subset is actually 3. Right, so we are going to use the find function which will give us the parent of the subset the element belongs to, right? The second operation is the very important operation which is known as the union operation, and what it simply does is it combines two subsets, right? It will just combine two subsets. So let's suppose I want to make another subset which is a combination of these two given subsets. So that subset is going to be 0, 1, 2, 3, 4 and 5. So this whole subset can be formed by using the union, and what union does is it combines two subsets. And the strategy that we are going to use in the algorithm is that instead of actually adding it inside of another subset, what we can do is we can actually point the parent of one subset to another, right? So this is a very good strategy. So we are going to use this union operation, and what it will essentially do is it will just point the parent. So you can see the parent in here is 3. It is just going to now get changed to 5. So that way we can achieve that also, right? So now we are going to see how logically we can actually divide a given set in the partitions or given subsets using these two operations, which is find and union operation, right? So let's start with the algorithm part. So first of all, we are going to assume that we are given a set which is here 0, 1, 2, 3, 4, 5. The first step is to create a set which we will call as the parent set. And initially this parent set will contain all the items which are originally there inside of our given set, which means that each of these elements represent that each and every element is initially a subset of its own, right? So here, after we do this, we are going to get a logical representation something like this. So we have 1, 2, 3, 4 and 5, and they all are actually now subsets. So you can see that this parent array has position 0, 1, 2, 3, 4, 5. So 0 is the position, right? So let's assume that this is I. So the I is the position, and if the position is equal to the item inside of the parent, we are going to say that this is the actual parent of this node, right? So 0 is a parent of itself, 1 is a parent of itself, 2 is a parent of itself, and so on. Now we are going to change these values according to the parent so that we can obtain these subsets, right? So let's see how we can do that. So the first step is done. We have created a parent set, which is actually just a representation of all of these subsets initially, right? So now let's say in this given set, I want to, you can see, achieve this type of partition. So if I want to create a subset 1, 2, 3, I will first have to combine 1 and 2, right? So in the second step, I want to combine the elements 1 and the element 2, right? So we can only combine one item at a time. We cannot combine 3 times, right? We can first we will combine 1 and 2, and then we will combine 3, right? So if we want to combine 2 elements, it can be 1 or 2 elements, and it can be subsets also. So whenever we want to combine 2 elements, the first operation that we are going to perform is find 1 and find 2, right? So these are the two elements that we need to perform, and find 1 and find 2 are basically the are going to find the parents of 1 and 2, right? So whenever we want to combine 2 elements or 2 subsets, we first find out the parent of that subset, because that is the only key of this algorithm, because we are only going to combine the parent of the 2 subsets or the parents itself, right? So you can see find parent of 1 and find parent of 2. We can find it from here in the given parent set. You can see that the parent of 1 is actually 1. So this will give me a value of 1, and let's say I store it in the value of x. So x is equals to 1 and y equals to 2, right? So y is actually representing find 2. So 2 is a parent of itself, so that's why the value of y is 2 here. Now what I'm going to do is, the next step is to perform the union, which we know is to combine these two sets, right? Which is 1 and 2. Now remember, the union function combines two subsets, but it actually does not combine two subsets, it combines the parent of these subsets, right? So 1 and 2 are the actual values. So the operation that we are going to perform here is parent of first position is going to be equal to 2, or generally I can write it as if we want to perform the union of x comma y, I will just assign parent of x equals to y. Now let's understand why we are doing this. So once we perform union 1 2, which is to actually write the parent 1 equals to 2, let's see what our parent array is going to look like, right? So 0 will remain the same. Parent, the first position is going to be equal to 2, so instead of 1 I am going to write here 2. Then 2 will remain same, then we have 3, then we have 4, then we have 5, right? So we have obtained this set here, or this array here. Now you can observe that in this array we have one set which is 0, we have another subset which represents 2 comma 2, and actually here we have 1 comma 2, which are the positions. Since these two are equal parents, we are going to say that these two are under the same subset, and then we have another subset which is 3, 4 and 5, right? So what essentially this means is that 1 and 2 have the same values, which is 2, right? So it means that they belong to the same subset, and 2 means we have assigned the value 2 here. We could have assigned it 1 also, but we have assigned it 2 here because we want to make the later one as the parent, right? So I am actually trying to make this one as the parent value, right? So what this now represents is that 2 is the parent of this whole subset, and since these have equal values, they belong to the same subset, right? So you can actually see here that what we are actually trying to do is we are actually trying to logically form subsets of a particular given set, right? So if you are given this set here, now you can see that I have logically divided it into 4 subsets here, which is 0, this is 1, and this is 2, then this is 3, this is 4, and this is 5. So 5 subsets are there now. Now what I want to do is I want to insert 3 inside of this one, right? So here you can see I have this subset 1 2 3. So if I want this subset, I will have to make sure that this 3 subset, I will have to combine these two, right? So let's see how I can do that. Again, we are going to follow the same thing, which is what we want to do is we want to actually now combine that. Now what we want to achieve is we want to combine the subset 1 comma 2 and the subset 3, right? So let's see how we can do this. The first thing that we need to do is find 1 and find 2, but remember that find is actually going to find the parent, right? So what I will do is, instead of combining 1 and 2, the parent of this set is actually 2. So what I am trying to do is I am trying to combine 2 and 3, right? So if I say combine 2 and 3, the first thing I need to do is find the parent of 2 and find the parent of 3, right? So what is the parent of 2? Here you can see from the parent array, at the second position the parent is 2. So if both the values that we are given in this find function are equal, we are going to say that it is the parent, right? So here I am just going to write the algorithm or the definition of the find function, or let's say it is a find parent function. We are given some element, let's say a. The first thing that I'm going to do is I'm going to check whether the value of a is equal to find, not find, it should be the parent array, right? So we have this parents array, and I'm just going to check whether it is equal to the value which is given here. So you can see here, if a is equals to parent position a, it means that we have the element is already the parent of itself. So in that case, I am just simply going to return the value. So return a is going to actually return the parent itself, right? So if that is not the case, which you can see here, that now if you consider the first position inside of the parent here, you can see the value of a, if I will choose it instead of find 2, if I will write find 1 and find 3, it will also be a same thing, right? right? So these two are actually the same thing, right? You can actually do this one or you can do this one. So if you do the first step, which is find 2 and find 3, 2 is the parent of itself and 3 is the parent of itself. So the value of x will be 2 and the value of y will be equal to 3, right? But in the case of find 1 and find 3, you can see when I will call the function find 1, the value of a is equals to 1, right? So a is equals to 1 here. And what is the value of parent of a, which is parent of 1? So at the first position you can see the value is 2, right? So I'm going to write here that the parent of a, which is 1, is equal to 2. So now you can see that this condition, which is if a is equals to parent of a, is now false because 1 is not equal to 2. In that case we will write the else case, right? So what we just want to do is we want to reach the parent node, because we can only perform the union operation on the parent nodes only, right? So you can see here these two are the parent nodes only, then only we can actually combine the two subsets, right? In the first case, since find 2 will already give the parent, which is 2, we have returned it, and in case of 3 also it is the parent of itself, so we do not have problem there. So the value of x becomes 2 and the value of y becomes 3. But if let's say you make a call to find 1 and find 3, the value of y you can see will remain 3, because find of 3 will actually give me the value of 3, because a is equals to parent of 3, right? So it will give me a value of 3. Now let's see what is the value of x. So in the else case, what I'm going to do is I'm going to actually make a recursive call to the find parent function. So what is the idea? The idea is very simple, that we want to reach the parent, because that's the essential motive of find parent function. It finds the parent of any given element inside of any subset, and once we have found out the parent, we can actually do the combining part, which is the union part, right? So find parent, and I will give the value a here, or I should write here this is a function. Inside this I will give the value itself, which is parent of a. So take a look at this important line here. What we are doing here is making a recursive call, right? So find parent of a. Now you can see that initially we were calling the find parent function with a value of 1, and since you can see a is not equal to parent of a, 1 is not equal to 2, we are making a recursive call on the parent of a. So here you can see parent of a is actually 2 here. So now this will make a recursive call to the find parent, right? And instead of a, I am giving parent of a, and you can see parent of a is actually 2 here, right? So it is now going to give the value 2. So find parent of 2 is actually 2 itself. So again it will come here, right? So the recursive call will come here. The value of a is now equal to 2 and parent of 2 is equals to 2, so it is going to return the parent, right? So this is a very important step here, which I am going to mark it as a star here, because it actually returns the parent. We are making recursive call, and at each recursion I am actually giving the parent of the given node, right? And we are not going to return the value until and unless we obtain the values of the parent, right? Until and unless the value that we are passing is equals to the parent of a, we are not going to return out of this loop, out of this function, right? So now you can see here the value of x will be equal to 2. So irrespective of what call you make, the value of x and y will remain same, and as we know that the next step will be union of 2 comma 3, and we know how to combine 2 3. We will just use parent of x, which is 2, will be equal to 3. So now the parent set is going to look something like this. The first element is 0, the second element is 1, the 0th element is 0, the first element has become 2, but the second element has become 3, the third element was already 3, and then we have 4, and then we have 5 here. So this is now our parent set after combining 2 and 3. So what can you see here? From here you can see that 0 is a subset, right? At 0th position we have a subset. At first position we have a parent 2. So here if I will show you that we have 2 here, and 2 is the parent of 1, and here you can see at if we go to the 2 position, the second position says that 3 is the parent of 2, so 3 is here, and then at 3 we have the parent, so we are going to say that this is actually the parent, right? So we have obtained this whole subset here 1 2 3 which has 3 as a parent, and similarly we will do the same step with 4 and 5 also. We are going to call these functions. Alright, so let's see how we can use the find union algorithm to detect a cycle in an undirected graph. So basically we are going to apply the same concepts, and if you haven't understood any concept before, you will understand with the help of this example. So it is undirected graph. So let's take a very simple example of a graph, which is, let's take only just 3 elements inside of this graph, which has these 3 elements, and let's make it a cyclic graph. Now we want to use find union algorithm to actually just find out whether there are cycles in a graph, and let's add some more elements like 3. So what is the idea? The idea is very simple. What we are going to do is we will pick up any one node, right? We will start picking up one and each nodes inside of this graph one by one. So initially let's say that we pick up 0 as the node, right? So let's say I have picked 0. Now what I will do is, after picking up 0, I will find all the neighbors of 0, right? So the next step is to find the neighbors, and we know that we can do that easily by traversing inside of the dictionary by using a for loop. And when we will find the neighbors, what we are going to do is we are going to add all the neighbors inside of a single subset. So you can see that 0 is connected to 1 and it is also connected to 2. So this will form one subset, right? So we are going to do the same with all the other nodes also. So we will do that with 1 also. We will find the neighbors one by one and we will keep adding them to the subset, which is like this. So 1 is connected to 0 and it is also connected to 2, then 3, and so on, right? We will do that for each and every of these subsets. So for each and every node, what I will do is I will find the neighbor. That is the step 1. The step 2 is that I will do a union of the neighbors and the node itself, right? So I'm going to do the union of the node and the given neighbor, right? So if we will have n number of neighbors, we are going to call this union function n number of times. And in order to perform a union, we will have to also write a check statement. We will have to first find the parent of the node and the parent of the neighbor, right? So find parent of node will actually give me what is the parent of that particular node. And if we want to find a cycle in a graph, we can actually use this condition, which is if the value of if the parent of the any node which we have picked is actually equal to the parent of the neighbor, right? Which means that if I will run this find parent function on, let's say, the neighbor node, and if these two values are equal, it means that we have actually obtained a cycle in a graph, right? So that graph will be cyclic. You can understand this condition. It is very simple. We will use the find parent function to find the parent of any given node, and if the parent of that node, that which we have picked, is equal to the parent of any of the neighbors, right? If those two parents are equal, it means that they belong to the same subset. So it basically means that it belongs to same subsets, and since they belong to the same subset, it means that it is forming a cycle in the graph, right? So let's see how we can write this whole algorithm inside of Python. Alright, so let's start writing the code for the given problem. So let's first create a main function here. So I will create a main function if name is equals to main, then we are inside of the main function. And now what I'm just going to do is I am going to create a graph data structure here, and this graph data structure is actually going to be a dictionary. So we will use these curly brackets here, and here what I'm going to do is I'm going to we will have 0 node, and 0 is actually has two neighbors, which is 1 comma 2. Then we have the second node, which is 1, and 1 is connected to 0, and it is also connected to, you can see here that 1 is connected to 0 and 2, but it's already there inside of this above set, so I'm going to leave an empty list here. Okay, so let's move on to 2. The node 2 is connected to 0 and 1, right? So I'm just going to write here, I'm going to leave this empty, and I'm going to write 2 here because 1 is connected to 2 and 1 is connected to 2, so 2 is also connected to 1, and here we have already mentioned that 2 is connected to 0, so we do not need to write anything inside of the 2 because it does not have any neighbors, right? It has been already covered here. So now what I'm going to do here is I'm going to create a class disjoint set, and inside of this class I'm going to first, we know that the first step is to create a parent list, and initially this list contains the all the nodes that we have. So 0, 1 and 2 will be here. So it basically initially represents that 0 is the parent of itself, 1 is has a parent of itself, and 2 is also the parent of itself. So if I try to access parent of 1, it will give me the value 1, and similarly 0 and 2, right? So these are the parents of each itself. So we have created separate subsets for each of these values. Now I'm going to define a function find parent here, and this find parent is going to take a keyword self and the value which is a, right? So here we will write the definition of the find parent function. So the first thing is we need to first case is that if the value of a is equal to self dot parent kth position, if this is true, then what we are just going to do is we are just going to return a, right? So we have already seen this case here, so it should be a here, not k, right? So we are actually returning the value of a here whenever we find that the element is there. Else what we are going to do is simply we are going to make a recursive call to the find parent function, and inside this I will pass the self dot parent a position, right? So we have already seen that inside of the introduction part. So here I'm returning this find parent is not defined, it says. So actually it is going to be self dot find parent, right? So we will have to use self to represent that we are actually creating to the object of disjoint class, right? So we will have to actually create a ds which is an object of this class disjoint set, and I will use this ds object to call these function find parent. And now let's move on to the next function, which is also very simple to implement, which is the union function, and it will also take 3 elements, which is self and a comma b, right? A comma b, or let's write x comma y. And we know that the simplest implementation is just assign the parent of this x will be equal to y, right? We have already seen this part also. So these are just simple representation of the parent function and the the find parent function and union function. Here we can also say instead of writing else here, I can just write that if self if a is not equal to self dot parent a position, then we are going to make recursive calls, right? So now we have these two functions ready. Now let's call these functions and let's make a call to these functions and see how it is going to look inside of a graph data structure. So first of all, we need to pick up one element from the graph. For that, we can actually use this simple for loop for I in graph. And now since we want to actually traverse the neighbors, we are actually going to use another loop for j in graph ith position, right? So what we are actually doing is we pick up an element from a graph which is at the ith position and we find out all of these neighbors. So j represents the neighbors at 0 position, 1 position and 2 position. So initially I will be equal to 0 because it's the first element of the graph, which you can see here we have picked it from this for loop. And now what we will do is we are fetching the value of j will be equal to 1 and 2. So what we want to do is we want to actually find the parent of 0 and we need to find the parent of j also and I, and then we are going to see whether they are equal or not, right? If they are equal, we are going to say that there is a cycle in the graph, else we are going to do the union part. So here what I am simply going to do is I am going to write I'm going to create a value x here, and this will be equal to ds dot find parent, and inside of this find parent I am going to actually pass the ith value, right? So we will find the parent of the node that we have picked and the parent of the neighbor also, right? So here I am going to write a comment here that we are actually calculating the parent of node, and here we are actually trying to find the parent of neighboring node, right? Or just parent of neighbor. Now we know that if the parent of this node and the parent of neighbor, if these two values are equal, it means that these two have the same parent, and if they have the same parent, it means that a cycle is being formed. So what I'm just going to write here is a case that if the value of x is equals to the value of y, right? So make sure to leave the right indentation here also. It should be inside of this for loop, and if x equals to y, I'm just going to print here that it is a cyclic graph, right? Else what we are going to do is we are going to take the union. So I'm going to call the ds dot union function, and I'm going to pass it two values, which is x comma y, which is not x comma y, yeah, it's x comma y, which is the parent. So remember that the union function is going to make the union of two subsets, and make sure you give the parent and not the element, right? So you cannot give the value of I, j to the union. You will have to find the parent of I and the parent of j, and then you will have to give it to the union function, right? So this is the whole program. So here you can see that we are actually going to run this program, and let's take a look at whether it is running properly. And I'm just going to run this file to see what is the output of this find.py file here. So you can see it shows that it is a cyclic graph, right? We are going to study another variation of find union algorithm, which is union by rank. Now this is actually an optimization over the algorithm that we have written in the previous tutorial. So take a look at this Python program that I have already created here in the previous tutorial, where we have seen that this is actually the find parent function, and here we have the union function. And we know that if we want to do a union, we will first have to calculate the parent of x, then parent of y, and we can do so using the find parent function. And then what we were traditionally doing is this step here, we were assigning the parent of the smaller subset to the parent of the larger subset. And here you can see that what will happen if the x is basically having more elements than y, then in that case we have not actually done any optimization, so we'll have to see that case also. So there comes the union by rank. So first of all, here you can see that I have created an array 0 1 2 3 4 5. These are the elements. So basically here I am going to write that we have initially a given array which is 0, 1, 2, 3, 4, 5. We have taken this same example in the previous tutorial, and here we want to create three subsets, which is 0, then 1, 2, 3, and then 4, 5. Right, so these are the three subsets that we wish to create, and here you can see that we can do so by combining 1, 2, 3, and then 4, 5. So in the algorithm itself, you can see I've made a call to this union function, and first we connect 1 and 2 inside the same subset, then 2 and 3 are in the same subset, and then we just include 4 and 5 in the same subset by assigning 5 as the parent of 4, right? So here you can see that self dot parent x equals to y parent, right? So I'm going to write here that traditionally in the find union algorithm, we were actually making a call of parent of x becomes equal to y, right? And here we were not dealing with the cases what will happen if the x has a subset which has larger number of elements than y, right? So let's see how the structures will change when we have these two cases. So the case one that we are actually going to deal with is that x has lesser number of elements than y. Or what we will do is we will keep assigning a rank to each and every node, and we will compare this rank, that if rank of x is less than the rank of y, this rank is actually a variable. Initially in the union by rank algorithm, we will create a rank variable which is assigned as 0 for all the subsets, and then we will keep assigning the ranks to the nodes according to how many elements are there in the subset. And then what we will do is we will compare those two. And so the first case that we have in here is what will happen if the subset x has a lesser rank than the subset y, right? Which basically means that x has lesser elements than y. So in that case, you can see that first initially we have here parent as 0, 1, 2, 3, 4, 5. After I make a call to union 1, 2, which you can see here, I've done here, I've made a call to 1, 2. You can see that 1 and 2 both have equal ranks, which is 0 and 0. So what we will do is, we know that if we do the union, the parent of x become equal to y. So x is equals to, actually here I'm going to write, in the first case we have 1, 2, and we will calculate the parent of 1 and parent of 2, which will be x parent and y parent respectively. So x parent and y parent are basically the parent of 1 and 2. So both of them has parent as itself, so they are going to be equal. 1 and 2 are here. So x parent is 1 and y parent is 2. If I do union using this case, which is parent of x parent equals to parent of y, what we are doing is, at the first position I will assign a value 2 here, right? So this is the 0th position and this is the first position, and it will become equal to 2. And then we have this type of structure here, and here if you want to see this visually, you can see that this is the 0th element. The first element has a parent 2, so I'm going to write here that this is the first element and it has a parent 2, right? And 2 is the parent of itself. The third element is the parent of itself, and similarly 4th and 5th are parents of itself. Now what will happen if I again make a call of union 2, 3, because I want this third node to get included inside of this subset, which is here, right? So this is what I want to do. I want to join a 3 inside of this subset which is given here, which is the actual desired result. You can see here we want 1, 2 and 3 in the same one. Now what will happen if we use this assignment, which is parent of x equals to y? So you can see here that x parent, the value of x parent is actually going to be x is 2, and you can see 2 is the parent itself, and similarly y parent is also going to be equal to 3. Now what we are doing is we will have to change the values inside the parent, right? So now 0 will remain same, 1 position has 2, so the position 2 will hold the value 3, so it is now going to be equal to 3, and the rest of the array remains same, right? So now let's take a look at how the structure is going to change here. So you can see we have the 0th element, the first element has a parent 2, the second element has the parent 3, right, and the third element is the parent of itself, and then we have the fourth and the fifth element. And now we can join these two elements by making a call to union 4, 5. One interesting thing you can note is that when we are trying to use this approach, which is parent of x equals to y, here you can see it is causing a problem because it creates a linear structure, and this type of structure, it looks like a linked list, and it has a worst case time complexity of big O of n, right? So instead of inserting 3 to this subset, which is 1 and 2, right, we are actually inserting the larger subset. In this case here I am going to write that we are inserting larger set to the smaller set, right? And this has happened because we have chosen this assignment only, and we were not considering that x is lesser than y or not. You can see the value of x, the number of elements or the rank of x is actually greater here in this case, because you can see that this is actually x and this one is actually y, right? So x is this subset. So if we try to involve in this case, in case 1, if we try to do this, you can see that we are going to get a result something like this, which is a linear structure. So instead of inserting a larger set to a smaller set, you can see we will encounter this problem that we will get a time complexity of big O of n, right? So we want to avoid this thing. What we want to do is, if we have 1 and 2, we do not want to make 3 as the parent, 2 will remain as the parent, right? And we want to insert 3 here like this, right? For that, you can see I will have to make an assignment parent of y equals to x, right? So on the basis of rank, we will have to decide out of these two statements, or let's say that these two equations, which is 1 and 2, we will have to make the decision of what assignment to choose on the basis of rank. And basically rank is actually showing the number of elements inside a subset, and we know that if we try to insert a larger set to a smaller set, it is going to actually create a time complexity of big O of n. But if we do the opposite, you can see this looks like a binary data structure, and it will actually have a time complexity of big O of log n. If we try to insert more elements in this array, instead of making it as a parent, we will keep inserting more elements. Let's say I want to insert 4 also here, then it will come here, and similarly we are going to do this with other elements also, and trying to maintain this time complexity of log n. Now let's implement this in Python in this program itself to see it in action. So first of all, this statement is actually ambiguous. We will only do this type of assignment will be done. You can see what we are essentially doing in this assignment is actually we are attaching you can see that this x parent is a lesser subset, it has lesser number of elements, so we are attaching a lesser amount, the lesser subset to the parent of y, which is actually greater, right? So we will do this case only by using a rank. So first of all, first things first, I will have to, right, so here we will have the rank array, and initially we will assign the rank as 0 for all of the items. So 0, 0, 0 like this. And now what I am going to do is, this assignment, which is assigning the y parent as x parent, will happen only when we have x lesser than y, right? Only if the rank of x, right? So here I am going to say if the self dot rank, right, if rank of X parent is less than the rank of Y parent, then only we are going to do such type of assignment, right? So if the rank of X parent means that the number of elements inside of X is lesser than the number of elements in the subset Y, we are going to assign the parent of X to Y, right? So we are going to attach the smaller subset to the larger subset, and you can see X parent is the smaller subset here, and it has a parent of the larger subset, right? So we are trying to attach the making the parent of the larger subset will remain same. You can see Y is parent here, and here also you can see Y is parent, and self dot parent X parent equals to Y parent. And this actually means, here I am going to write a comment here, that in this case we are attaching smaller tree to the larger one, right? So we are doing that because the rank is lesser. Now we are going to move to the next case, which is here. So I will write elif the rank of X parent is greater than the rank of Y parent. What this means is that the number of elements inside of X is large and the number of elements inside of Y is lesser. So in that case we are going to attach the smaller tree to the larger. So for that we will actually use a parent, right? Since we want to assign the smaller one to the larger one, we will first write the smaller here, which is Y parent. According to this condition, you can see that Y parent has a lesser rank, so lesser rank subset will be assigned to the larger rank, like this, right? Now let's move to the last case. What will happen if we have two subsets which are equal in ranks? You can see initially we have elements 0 0 0 0, so initially two of them will have the same rank. So in that case we can do anything, we can assign any one of them as parent. So I will assign the parent of, let's say, X. You can choose any one of them, right? You can make any one of them as parent, as I'm making X parent here. Now remember that whatever element you are actually attaching it, you can see that I'm making the X as the parent and Y as the parent of X. So you can see here that Y is parent of X, right? So if Y is the parent of X, I will increment the rank of the parent, right? So whenever we attach a child node to the parent node, we increment the rank of the parent by 1, right? So here I am going to write self dot rank Y parent, which is the actual parent, is plus equals to 1, right? So I'm incrementing the value of the rank by 1, right? So here we have this type of structure. Now let's see what is going to be the output of this program. All right, so you can see here it shows 0 2 2 2 2 5 5, right? So it means that we have the 0th element. 2 2 2 means that let me show you this structural. Here we have the parent array. So the parent is now going to look like 0 2 2 2 5 5, right? So what this means is that we have a 0, the parent is 0 at the first position, right? So I will write the positions here quickly. So the first position says that the parent is 2. The second position says that the parent is 2. The third position says that the parent is 2, right? This is actually important because this has happened only because we have assigned the rank according we have done this assignment according to this rank here, which you can see, right? So we have assigned this one here. So this has happened only because of rank. So we will increment the rank by 1 whenever we have the ranks equal, the ranks are equal, then we are going to increment the rank of the parent by 1, and then we are actually comparing it. In these two cases we are actually trying to compare, and here you can see we have obtained this structure, and this is actually an optimal structure and is better than this one, right? So this is not a good approach, while this is actually done using union by rank. So this is the concept of union by rank. So in the next tutorial we will use Kruskal's algorithm, and in that we are going to use this strategy union by rank to find the minimum spanning tree. In this video we are going to study the Kruskal's algorithm. In the previous tutorials we have covered find by union algorithm, and in this tutorial we are going to use that algorithm also in this tutorial. So basically we are going to use Kruskal's algorithm, which is actually a greedy algorithm to find the minimum spanning tree, which is MST here. So first we need to understand what is a minimum spanning tree and why we are actually calculating the minimum spanning tree, and then we will see how we can actually use the Kruskal's algorithm to find out the minimum spanning tree. So first of all we are given this graph here. So you can see here we have these 5 vertices, and you can see that the edges are also weighted here, so they do have some distance in them, right? So first of all we know that in a greedy algorithm we at each and every step the algorithm will try to find a greedy approach, which means that let's say there is a problem which says that we want to minimize the cost to reach from one node to the another. Then at each and every step the algorithm will automatically become greedy, and it will start choosing the distances which have minimum distance in the adjacent nodes, right? So this is some kind of approach which is used in greedy algorithm. So before coming to the minimum spanning tree and the Kruskal's algorithm, first let us try to understand what exactly is a spanning tree, and for that I am not going to consider this complex example. I will create a very simple example so that you will understand this very well. So here you just need to consider these 3 nodes which has this type of graph, right? So very simple graph. Now in this graph a spanning tree, which I am going to write here. Alright, so let's try to understand what is the spanning tree. The spanning tree will have all the vertices exactly as same as the graph, but the number of edges will be vertices minus 1, right? So we will have vertices minus 1 edges inside of a spanning tree. Now what is the reason why are we getting vertices minus 1 edges? So here you can see we have 3 vertices, so basically we will have only 2 edges. So what is the reason why we have only 2 edges? Basically a spanning tree says that if you start from a node, you will have to cover all the nodes, but you cannot form any cycle in between, right? So let's say that we start from 0, then we reach 1. Now you can see 2 is not visited, so now we will have to visit 2. Now after you have visited 2, you can see all of them are visited once, and so we are not going to connect this edge, because if we connect 2 and 0, it will not be a spanning tree as it will form a cycle. Similarly, you can see here there are some cycles in the graph. So a spanning tree is actually the same structure, but the number of edges will be vertices minus 1. So there will be a 1 less vertex in the graph given below, right? So this graph here, it has 2 edges only. So let's construct some more spanning trees. This is also a spanning tree of the same graph. Let's connect 0 to this time. After connecting 0 to, I can connect 2 and 1. Now I will not connect 0 and 1 because it will form a cycle, right? Let's construct one more possible spanning tree. This time I am going to connect 0, 2 and 0, 1. So you can see we will have multiple spanning trees of this given graph. Similarly, for this given graph, we will also have multiple spanning trees. Out of these spanning trees, which you can see here, these three spanning trees, we will calculate the cost in each of these cases. So let's assume that we have x, y and z distances, or you can say these are the weights of the edges in this graph. We will just have to calculate the cost here. So the cost here in this case will be xz. In this case it will be x plus z, right? So the cost will be x plus z. Here it will be y plus z, and here it will be x plus y. Out of all these costs, which one has the minimum cost, that is going to become the minimum spanning tree. So out of all the spanning trees which we have constructed of a given graph, the one which has the minimum cost is known as the minimum spanning tree. Alright, so what is the use of minimum spanning tree? Why we are calculating a minimum spanning tree? Well, the idea is very simple. We will have a spanning tree. It means that we have visited all the elements. There are no cycles. Plus we have the minimum cost, right? So we have achieved the objective, which is to find the minimum cost while traversing all the vertices, right? So that's the main reason why we need to calculate minimum spanning tree. So let's say if I want to go from 0 to 2, I have the distance. So in this manner we are going to use minimum spanning tree to even find the shortest path inside of a given graph, right? Now we are going to see how Kruskal's algorithm is used to find this minimum spanning tree, right? So this is a question here, that if you are given a graph and you want to write an algorithm, how will you write the algorithm to find the minimum spanning tree? So we are going to use Kruskal's algorithm, and we will also implement the same algorithm in Python also. So first of all, let's try to understand how Kruskal's algorithm works. Step 1 is to basically sort all the edges according to their weights and in the ascending order, right? So out of all of these edges, which one has the minimum cost? You can see this one is the minimum distance. So I'm going to make 3 columns here, which is weight, the starting node, which is u, and the ending node, which is v. Out of all these, I have the minimum weight 1. Then we have u and v, which is 2, 4. Then after 1 we will have 2, and 2 is actually 1, 4. After 2 we will have 3 here, so the weight is 3 and the elements are 2 and 3. Remember, the graph has to be undirected. Then we have the next distance, which is 5. Then similarly we have 8, and then we have 11. For 5 we have 0, 1. For 8 we have 1, 2. And similarly for 11 I have 0, 3. So the first step in the Kruskal's algorithm is to sort all the edges according to the weights and in the increasing order, right? So you can see that the weights are in the increasing order, right? And we have these elements here. These are the actual edges. So 2, 4 is an edge, 1, 4 is an edge, and similarly we have all of these edges. Now let's move on to the second step, which is a very important step. It includes find union algorithm, and in the section 7.6 and 7.7 I have already covered the find union algorithm and how to optimize the find union using the find union by rank. So you can watch these 2 important lectures and then you can continue from this step onwards, because step 2 will require the knowledge of these 2 tutorials. So make sure to watch them first. It is included in the current playlist. I will give the link to the playlist in the description below, so you can check that out. Alright, so let's move on to the step 2, which is the last step of this algorithm. And in the step 2 we are going to use union find algorithm, and this algorithm is basically used to detect cycle in a graph, right? So we have already covered them in these two lectures, how to detect cycle using union and find. So the Kruskal's algorithm says that once you have sorted all the edges according to their weights, start picking the edges one by one from this list, right? So first of all, I will sort them using sorted function in Python, and then what I will do is I will start picking them one by using a for loop. So here we will have the first entry, which you can see here, which is the edge 2 4, which has the weight 1. So we are going to pick up this one, and what we are going to do, we are going to do the union of this 2 comma 4. Now what union of 2 comma 4 does is it will put both of them in the same subset, right? So 2 and 4 will come in the same subset, and we know that whenever we are actually doing the union, we are doing the union of parent of 2 and we are doing the union of parent of 4, right? This comes from the knowledge of 7.6 and 7.7. So whenever we are doing the union, we are actually doing the union of parent of 2 and parent of 4. So once we have done these union, what we will do is we are only going to do the union when these two parents are not equal, right? So I'm going to say that if parent of x, and let's assume that this is x and this is y, if parent of x is not equal to parent of y, then only we are going to do the union of x comma y. So we first need to find the parent of x, then the parent of y. So here we will first have to find the parent of 2 and the parent of 4. If both of them have the same parent, we know that they actually are forming a cycle, and if they are forming a cycle, we are not going to do the union, right? So that's the main logic of the minimum spanning tree. That's why I have drawn that those diagrams here to show you how important it is to detect cycles in a graph. So we are going to use union find algorithm. We know that if we want to find the parent of any element, we will use the find parent function or simply the find function in the union find algorithm. So once we have done this, we will keep doing this with other elements also. I will calculate the parent of 1 and the parent of 4. If both of them have different parents, then I am going to do the union of them, which means I am going to combine these two subsets, which is 1 and 4. Then similarly I will do with 2 3, then 0 1, 1 2 and 0 3. So after the end of this algorithm, what we will obtain is whenever these two parents are not equal, we are going to do a union of them, and we are also going to print x comma y, which means that if the parents are not equal, then the edge is part of the minimum spanning tree, and if it is the part of a minimum spanning tree, I am going to print that out, right? So let's see after the end of this algorithm how the minimum spanning tree will look like. Alright, so let's follow the Kruskal's algorithm. First step is to pick up 2 comma 4. So here we will connect 2 and 4. The distance is 1, which is here. Since we are connecting them, we are actually doing the union of them, right? And you can see that their parents will not be equal since there is no current cycle in this graph. Then I will pick 1 and 4. You can see 1 and 4 is here. I can connect 1 and 4. We will do the union of these. We will check whether the parents are not equal. You can see the parents will obviously not be equal because there are no cycles, right? So they will do the union. Now let's move on to 2 and 3. So we will connect 2 and 3, and the distance, which is the weight, is 3 here. Again we are doing the union because you can see there are no cycles yet. Then we have 0 and 1 and the distance is 5. So if I connect 0 and 1, you can see there are still no cycles here, so I can actually connect 0 and 1 and the distance that is going to come is 5. Now at this point you can see all of the nodes are connected, right? So this step 2 is actually going to run This whole step will run until and unless we have visited all the nodes, right? So if we have visited all the nodes, we know that this is the minimum spanning tree that we have obtained here, right? So you can see that the total cost will be 3 plus 1, which is 4 plus 2 6, 5 which is 11. So you can see this is the minimum cost that I obtained from this minimum spanning tree, which we have got by doing the union and by sorting the whole graph according to the edges and their weights, right? So this is how this algorithm will work.